This conference will now be recorded.
Okay, so the plan is afterwards we download it on YouTube and give a link to anybody who'd like to see your presentations and discussions. Okay, Kiss, I think it's all yours now.
I think you are muted, Keith.
Kiss, switch your microphone on.
Okay, sorry about that. Can you hear me now?
Yes,
we can.
So I'd like to explain a bit about how this came about, or how the original workshop where we were going to meet face to face came about, and what I'm hoping the various people that I've managed to persuade to give presentations will contribute. So the 3D printing and porous sound absorbers offers a good new opportunity. Well, I say new, people have been working on it for a few years now, but one of the problems is to do with the fact that, well, the opportunity it offers is that you can actually design a microstructure to give a target performance. And that's quite exciting because otherwise you have to do lots of things in terms of mounting and air gaps and so on in order to achieve a given performance with a regular sound absorber. The problem has come about because although you've designed this microstructure, when you try and make it, when you try and 3D print it, there are lots of imperfections. And we're going to hear a bit about that both from Thomas Zeninski and from the Le Mans people, Theo Cavaliero and Jean Bouvert. And we're going to hear also about what 3D printing manufacturing methods are available from Thomas, and about a round robin done on what can be achieved with the different 3D printing technologies. Thomas and others, because of the fact that they have good numerical methods for doing simulations of quite complicated microstructures, have looked at creating quite complicated microstructures. And to some extent, we need to know what it is about a microstructure that's going to influence the sound absorption. And that's why Camille is going to give us a talk to explain all these things. And then I'm going to point out, and so will Philippe Leclerc, that actually quite simple microstructures can achieve quite good acoustical performances. And Philippe's microstructures are based on modifying the effective complex compressibility of the material, and mine are based on modifying the tortuosity in the material, which is important if you're trying to create a good absorption from a thin layer. And then I also thought it would be good because I can see that these days you can't be a single discipline anymore in order to get the interest of industry. You've got to have lots of arrows to your bow, so to speak. And so Andrew Kennedy has kindly agreed to talk about how you can achieve multifunctionality and what that means. Okay, so I think now I can go over to Camille and stop sharing, if I can figure out how to do it.
Must be in the top right corner, a little icon to click on it. It's called screen.
Sorry about this. I'm very slow. Stop sharing screen. Okay, you did it for me. Over to Camille.
Okay, hello everyone. Very pleased to be with you today. Thanks for the invitation. Can you hear me correctly?
We can hear you, Camille. If you make your screen full screen. Oh, that's it. Yeah, that's it.
Okay, good. Thank you. So the suggested title of the talk is Microstructure Parameters Influencing Acoustical Performance. What is at the heart of acoustical materials, from my point of view and my own experience, is dealing with three important aspects, which are structure, or local geometry features, properties. We can speak about acoustical properties. We can also think in terms of thermal properties, structural properties. Here we will deal essentially on transport properties, which are relations for sound absorption properties. And of course, there is also another important aspect of this problem.
Please, sorry, Camille, please will people who are joining mute their microphones?
Yeah.
Bana yani 10 dakika sporunu yapsan iyi olur oğlum. Tamam mı?
So the last aspects of this, general picture is the manufacturing process. From my point of view, I mean, from the experience I had during the past, I was dealing with industrial problems where the manufacturing process is not 3D printing.
Talking about the structure of the materials.
I will show you some examples which are not directly connected to 3D printings, but I think that from this experience we can try to elaborate on what is important in terms of microstructural parameters influencing acoustical performance. So we'll try to skip on the next slide. Here is a rather classical slide. The motivation is that fibrous media or foams or granular media are known to be able to mitigate sound from their transport properties. I mean, microstructural and transport properties. So basically, we are interested in linking microstructures with transport and acoustical properties, whether we have a periodic random microstructure. So the problem will be, in a way, more easy to deal with for 3D printings, because in essence, we are dealing with periodic microstructures, and you will see that it's convenient for the classical numerical methods, which are now well established in the field. So basically, one of the methodology which has been greatly used in the field is to generate a representative volume element of the porous media, the porous microstructure, assuming a scale separation, which means that the wavelengths for audible frequencies is greater when compared to the sample scale, and also when compared to the characteristic features, characteristic scale of the microstructure, basically a pore size, typical pore size. And another assumption could be, but is not, doesn't has to be firmly respected, is the rigid frame assumption. Then you can solve transport equations, or basically boundary value problems, and by field averaging the solution fields properly, you come out with transport parameters or macroscopic parameters, and then you can link microstructural features you get at the lower scale from your representative volume element with the transport parameters you obtain from these numerical approach. It could be also an experimental approach, but this method provides you with a film link, because there is a unique solution from the local geometry level to the macroscopic properties. And then, if you want, and this is generally what is made when you are dealing with an industrial problem, you establish some micro and from microstructure to macroscopic relationships in order to get a kind of mapping in between local geometry parameters and transport parameters, which gives you the sound absorbing behavior. And from this mapping, this provides you with a kind of surrogate model, which is suitable for optimization purpose. Here today, I'd like to focus not especially on the numerical aspects, which are now quite well established in the community, but rather on another point of view. I think it will be interesting to introduce this point of view for this seminar. And the main message is, let's try to establish continuous dialogue in between imaging techniques, which provides you with the significant local geometry features having potentially an impact at the upper scale. So what are the imaging techniques? And then the model, the local geometry model, whether you are dealing with packing of spherical or aspherical particles, polyhedral tiling if you want to model foams, and distribution of, let's say, cylinders if you are tackling the problem of fibrous media. And then once you have established a model, or you have a potential representative elementary volume, you solve numerically the equations governing the transport properties you want to derive from this geometry, and you need a validation. Basically, the validation step should be independent of all the previous key steps, imaging techniques, and the candidate for a representative elementary volume, so that you can compare macroscopic properties or transport parameters which have been measured at macro scale with parameters and macroscopic properties which have been obtained from in an independent way just by solving the boundary value problems I introduced briefly previously. And if the agreement is good, then you have this kind of representative elementary volume, and you can go further into the optimization process. My point is that in a way this is the idealistic situation, and you will probably see during the talks of the other speakers that there is always a kind of adjustment to be done when comparing measurements with macroscopic parameters obtained from the local geometry model. And this comparison is fruitful. It is fruitful because the transport parameters convey some physical information, and by interpreting correctly and properly this physical information, you can go back to imaging techniques and see if you didn't miss at a first sight a microstructural feature which have a significant impact, and then you can improve your adjust your model. And during the rest of the talk, I will just show a few examples in order to illustrate this main message. And I think it could be a big picture for all the talks of this morning, because we are always dealing with this kind of methodology, I would say. So let's go back, but very briefly, to the basic equations governing the permeability, which is an important parameter governing the sound absorption behavior of porous material. Basically, you have to solve the Stokes equations, which govern the asymptotically low frequency behavior of your porous material. And by field averaging of the velocity field, which is a solution of this Stokes problem, then you can get a rescaled parameter, which is a permeability field. And when you average this permeability field through your phase field, then you get the permeability, which is a permeability tensor, which means that you can compute it in at least 3 different orthogonal directions. This is an important parameter for acousticians, which is basically the reverse of the resistivity times the viscosity of air. Another fundamental transport phenomena, which is transport phenomena we get at the opposite frequency range, in the high frequency range, is the basically the dynamics of the fluid when the fluid is non-viscous, when there are no viscous exchanges in between the solid frame and the fluid phase. And then all the physics is governed by potential flow equations, which is formally identical with electric conduction problem. And in terms of macroscopic parameters, we are dealing with basically two transport parameters: the tortuosity, which is expressing a dispersion of the local velocity when compared to the average velocity, and the viscous characteristic length. And you can see that the viscous characteristic length is a kind of generalized hydraulic radius, but it has been weighted by the sorry, the electric field or the non-viscous velocity field, which means that there is a strong effect of narrow pores, narrow constrictions, narrow interconnections in between two bubbles, two pores, and this is a signature of the smallest interconnection between pores. Finally, we can also deal with a third fundamental problem, boundary value problems, which is basically related to the dissipation of heat in the low frequency asymptotic regime. And from this boundary value problem, you can extract a last. This is not the only way to see macroscopic parameters, but another important macroscopic parameter, which is the thermal static permeability, which is basically the average of the excess temperature when solving this boundary value problem. All these parameters are included into the Johnson, Champoux, Allard, Lafarge model. And you have some simpler model, let's say Johnson, Champoux, Allard. You can get some connections in between these transport parameters, which are carrying a physics, and some other macroscopic or semi-phenomenological parameters. This is not the only way to describe physics, but this is an interesting way because you deal with macroscopic or transport parameters which are carrying a physics, and you can measure these parameters from direct and acoustical measurement techniques. Here is a way to measure these transport parameters or macroscopic parameters. Of course, a very important parameter is the porosity. And my experience is that you really need to try to get a very accurate measurement of porosity, because this is the first parameter you will be able to compare with your geometrical model. So if there is no agreement in between these purely geometrical parameters which have been measured and computed, it will be difficult to get this link in between microstructure and acoustical properties. Then you can measure directly the permeability or the resistivity from standard methods which are based on the Darcy law. And I would recommend measuring frequency-dependent response functions, let's say the dynamic mass density associated with visco-inertial effects, and dynamic bulk modulus associated with frequency-dependent thermal effects that you can get from a 3 microphone impedance tube setup, or eventually a 4 microphone impedance tube setup. And based on this, those set of parameters, you can get, so you have basically 4 input parameters, and you can get the remaining ones, which are the tortuosity, the viscous length, the thermal length, and the thermal permeability. What I can mention here is that—
Camille, you've got a couple of minutes left.
Yeah. Sorry. What I can mention here is that you could try to get the more macroscopic parameters you get from direct measurements, the better it is. And you should try to avoid, if you can, inverse methods based on minimization of the cost function, it's not always possible, and you can get also some flags in order to avoid some errors. But what I would like to say is that minimization of the cost function means that you have several possible solutions at the macro scale, and this means that you will get a proper description of your sound absorbing behavior. But because those macroscopic parameters are all linked together, this does not mean that it's strictly related to microstructure. You have a description at macro scale, but because you have no unique solution, if you minimize a cost function, it could mean that the sets you obtained are not directly related to the microstructure. So let's try now to give a few simple examples to get a kind of intuitive vision of microstructural features having a significant effect at the upper scale. Let's try to begin with a simple two-dimensional hexagonal arrangement of solid fibers. So the wave is impinging the sample from one of the perpendicular direction, X or Y direction, and you have basically three microstructural features to describe this very simple structure. You have the fiber radius, you have the pore size, which is associated here to 2L, and you have eventually fiber cross-section shape. What you can see when you are performing simulations is that the more important, or the first significant microstructural parameter is what is called W here, or the throat size, which is the smallest interconnection size between fibers or between struts, if you are thinking in terms of a foam. As long as you reduce or expand this characteristic size, you will basically increase the level of sound absorption up to an optimum, and then if you open too strongly, or if you reduce too strongly this interconnection, this throat size, then you will reduce the sound absorbing behavior. Then you can keep this throat size as being a constant size, the one which have been found previously in the range of, let's say, intermediate resistivities corresponding to a strong sound absorption level. And what we saw is that you have a kind of modulation of the sound absorption level, which means that eventually you can tackle some specific parts of the sound absorbing spectrum, but this is less impacting when compared to the throat size.
Camille, I'm sorry that you need to hurry up, please. I know you've got 20 slides to get through.
Yeah. How much time do I have?
You ran out of time, actually. So it's time you eating into your question time.
Okay. So I will just comment a few more slides, and then we can go on the question times. I really wanted to focus on the general message, which was this big picture about the relationships between microstructure, between measurements, and between computational aspects. So this is just a snapshot about the effect of cross-section shape, and the basic message is that you can get a waste reduction when you increase porosity with a quite similar sound absorbing behavior. So here I wanted to describe a study which has been carried out on gypsum foam, and from imaging techniques like microtomography, you can get some microstructural parameters, the pore size, which is dp here, and the throat size, which is dt. Based on these parameters, you can create a basic model, local geometry model, and here this is a kind of example of this interaction between microstructural information, macroscopic measurements, and the way you can adapt your model or refine or enrich your model. You see that the porosity you measure, which is the experimental porosity at the bottom of your table, is in the order of 0.86. And if you use a single porosity model, you only get 0.70 as a porosity. So you have to include the microporosity of the gypsum foam that you can see on the right side of the image in the middle of the slide. And by doing so, you are able to get the sound absorbing property of the material. One other important aspect in this examination of relationships is about the viscous characteristic length, lambda. And you can see that once you introduce the double porosity model,
I would have to switch you off in a couple of minutes.
Sorry?
I would have to switch you off in a couple of minutes because you got only 2 minutes left before next speaker have to start.
Okay, sorry. So just to conclude, I think that now the numerical approaches are quite well established in the field, and what could be important is to always keep in mind this the importance of this dialogue between imaging techniques, local geometry model, and measurements at macro scale, in order to be able to enrich the model and answer the question, what are the microstructural parameters having a significant effect? Thanks for your attention, and sorry for being timeout.
Keith, how do we clap over internet?
Yes, I think we just clap. Yes. Thanks, Camille.
Okay. Very nice, Camille.
Well,
that was me.
So, I mean, we actually almost ran out of time. And how much flexibility, Keith, we should give you this? Shall we let people ask a couple of questions?
Well, I think probably they can type a question which Camille can peruse, and then when we next get a discussion break, can answer at that point. I think we better press on really with the next speaker, because I think that what Camille has described is very appropriate to how you tackle trying to understand materials that are made by bulk manufacture. But as Whereas people will be suggesting later you can have a totally different philosophy if you can start from scratch in making the microstructure. I think that's the only thing I want to say. Let's go on to the next speaker.
That's good. Thomas?
Okay, I'm
well,
here.
By the way, the questions which you type, they also be recorded, guys. So therefore, they wouldn't get lost. You can continue to interact with the speakers even after the end of this discussion.
Okay, so should I share my screen? I believe it's like that.
Please do.
Okay. Okay, so can you see the screen right now?
Yes, and can hear you as well.
Okay, so I'm going to. Good morning, everybody. I'm really glad to participate in this event. This is kind of a new experience for me, and I'm going to talk right now about our experiences that we have had with my PhD student Kamil Opila when 3D printing different sound-absorbing porous materials. And actually, the title of my presentation is Periodic Sound Absorbers Made Using Additive Manufacturing Techniques. And the subtitle is Results of Round-Robin and Adaptive Absorber Studies. And here is the outline of my talk today. First, I'm going to say a few words about different 3D printing technologies, and then I will perhaps focus only on the one example of this kind of research. I will show you some results of a round-robin study on 3D printed porous media. I initiated this research activity within the framework of the Denons project, which is, I believe, well known in the community. And in February, I had a presentation in Coimbra. I will show you some slides from this presentation. Perhaps if time permits, I will have also a few slides for another research of that kind. Okay, so let me briefly explain the main principles behind the three main additive manufacturing technologies. The first one is the so-called fused deposition modeling or fused filament fabrication. There are usually more than one name for this recently developed technologies. And here you may see a picture which illustrates the principle, which is some kind of control, extrusion, and deposition of thermoplastic polymer filaments. The filaments are provided in spools. So here you have a spool of the material, and it is driven using, let's say, two gear wheels into a header, into a nozzle, which is heated up to a certain temperature. And at this temperature, the polymer melts down to a liquid state. And then when the nozzle is moved away, it solidifies. So we can 3D print a layer on the printing bed or on the previously 3D printed layer of the material. Actually, this picture illustrates a, let's say, dual nozzle device. So we can 3D print using two different filaments, which is important because we need to print sometimes technological supports. And we can use this second filament to print the supports because they are some kind of polymers which can be dissolved in a chemical solution. This is the very cheap technology, but the not very good quality because there's a low resolution involved. Usually the size of the nozzle is 0.4 millimeters. So another technology is the so-called stereolithography, SLA. This is the well-known, well-used acronym for this technology. And here we have a container which is filled with the liquid photopolymer, and we use a laser beam to solidify some small bits, let's say voxels of this photopolymer resin. We do it first on the fabrication platform, which is submerged in this resin, and it is moved down when the whole layer is 3D printed by a very small distance of the layer thickness, and the whole process can be repeated. After the process is finished, we need to take our object out from this resin unit. You see that we need much more material than only for the object. And then there's a second stage. We need to put this object into under the ultraviolet light to cure it. So there's some post-treatment involved here. But the advantage is that we have very fine prints with very high quality smooth surfaces, so much better quality than in the case of the FDM technology. And the third technology is the so-called selective laser sintering. And here we print using polymer powders or metal powders, and depending on that, your, let's say, sintering device can be extremely expensive if you want to print from metal. The principle is as follows. We have a container which is filled with the powder, and the powder supply platform is at its lowest position. It moves up by a very short distance of the layer thickness. The fabrication platform at the very beginning is at the top position in this second container. So it moves down only by this small distance, and the roller sweeps the powder, the first layer of the powder, onto the fabrication platform. Then we use the laser beam to 3D print the first layer. The platform goes down by the thickness of the layer. This one goes up, and the whole process is repeated. The main advantage of this technology is that we don't need supports, because the powder plays the role of the supports. But of course, after 3D printing, we need to take our object, we need to clean it. So for example, in case of our application, we need to take this powder out of the pores, which is kind of problematic. We need to wear masks and goggles. Okay, right now we are accustomed to that, but this is a very dirty technology. So these are main disadvantages. The quality of printing is comparable to the resin samples. Now I would like to show you the first example. This is the round-robin study on 3D printed porous media, and in this research activity I just invited people from different laboratories from many countries, and I just proposed that, okay, let us print the same periodic microstructure, the same periodic porosity, samples of the same periodic porosity using different additive manufacturing technologies, different devices, and let us measure them in impedance tubes for acoustic absorption and surface acoustic impedance, and let us compare the results. So there were many people involved. We have a publication which is under review right now. And the first geometry that I proposed is based on some kind of random arrangement of pores, or here you have an algorithm which at each time step we have a random arrangement, but periodic arrangement of such bubbles which may penetrate each other. So eventually, when the algorithm stops, because we decrease the size of the unit cell, and we stop the algorithm when the required porosity is achieved. It is computed at each time step. So what we got is for example, this kind of a periodic unit cell. So there are 4 pores here of different sizes, like with windows of different sizes. This is periodic, but generated in a random way. And I also proposed that we should maybe, by rotating this original cell, generate 3 different orientations that we used for our samples. And first I just checked these periodic unit cells for my slicer software for one of my FDM printers, and the size of this cell is 5 millimeters. And you see that using my software I can check if this cell will be printed correctly. And unfortunately we have a lot of red areas, which means that here, for example, we shall have additional window which is not present in the original design. This window will be smaller than the original one. a little bit rough perhaps. So in order to avoid this, I just decreased the diameter of all the pores by 10%, and then I used the original diameters of windows linking these pores for let's say cylindrical channels that link the pores that were previously linked by the windows. And now you see that this geometry can be correctly 3D printed, and obviously we put additional unit cell above here, so these red areas will vanish completely, and we generate this kind of three-dimensional array, 6 × 6 × 10, so the height of the array is 50 millimeters, and we cut out a cylindrical samples with a diameter of, let's say, 29 millimeters, that they say diameter of our impedance tube. And many laboratories did it. Actually, there were 9 institutions involved, but 6 laboratories actually manufactured their samples and measured them in the impedance tubes. But I also invited 3 additional laboratories to check the acoustical testing, the results of the acoustical testing. I'm going to show you only the results for the tubes, for the samples with the diameter of 29 millimeters, so the results from IPPT from Poland, from Université de Technologie de Compiègne from France, and from EMPA from Switzerland. You see that all the technologies are involved. There were a lot of 3D printers that were used to manufacture the samples. And for example, at my institution, we used even 2 different printers for FDM technology. So here you may see the top faces of the samples. My PhD student, Kamil, he printed using FlashForge Creator Pro. I used Zoltrax M200. You see that perhaps the surface of the samples of my PhD students are a little bit smoother than my samples. But anyway, we also manufactured samples using selective laser sintering from polymer powder, also from metal powder, some resin samples which are not presented here. I got the very nice photographs from UTC from France. These are FDM samples manufactured by Nicolas Dauchet and Thomas Boutin. And here, please take a look at these photographs, because you should notice there are some small fibers across these channels and pores. So really the quality of these samples is really much inferior to our samples, which will be actually very important when I discuss the results of sound absorption. These are very nice samples manufactured from resin using stereolithography. I treat them as some kind of reference samples with very nice, neat, smooth microgeometry. And UTC, they also printed samples from polymer powder, but with larger grains, not so fine as we used. So they realized that they actually have the effect of microporosities involved. So eventually, after measuring these samples, they also impregnated them and they measured them again. And this will be very interesting to compare these 2 results. Finally, the results from Switzerland, resin samples and metal samples, and the results of sound absorption. These are 2 curves manufactured using FDM technology, but different printers. I was quite astonished seeing that they are very similar, but when I compared them also with the curve for samples manufactured from polymer powder, you also see that the curve is very similar, although the technology is completely different. And then you have a curve for the metal sample, and you see here for these 2 peaks at higher frequencies, we have some kind of shift to lower frequencies, and this is because actually these samples were wrapped in a tape in order to avoid scratching the inside of our impedance tube. Okay, so then I got the results from France, and first I compared the results for the FDM sample, and I was quite unhappy to see that, okay, we have such large discrepancies. But then I look at the photograph and at the photographs, and I realized that there are these small fibers which increase the sound absorption, especially between the peaks. The first peak is well represented, by the other peaks are not so well represented, and there is a much larger absorption between the peaks. So this is because of the very bad quality of the samples. But then when I look at the curve for the samples manufactured from this black resin, it appeared that the curves are very similar to my curves. So they were very nice samples, much smoother than my curves, but it was not very important, it appears. And finally, I got some results from Switzerland, also a resin samples, very similar curve. And now maybe the most interesting results. These are these samples sintered from a polymer powder of larger grain, larger grains that we used, and there was microporosity involved. So UTC, they impregnated the samples and they measured them again, and you see that the curves are very similar, only at the highest level. They at the highest frequencies they have some discrepancies, which was expected. All the curves compared together, and now the absorption curves for the sample with an air gap between the sample and the rigid termination in the tube. Finally, the results for other orientations, because these were only for FPCX samples. These are the black resin samples from France, from UTC, and I asked Nicolas to send their samples to École Centrale de Lyon, and they measured this, so you see that the measurements are correct, acoustical measurements are correct. I did the same with my samples, and here you see that you may see that also my measurements were done correctly. It is important to mention here that I manufactured and measured my samples in early spring, and in École Centrale de Lyon they did the measurements in July. Okay, so I have some. Do I have some more time, or should I start a discussion?
You've got a couple of minutes left. Yeah. So
I will briefly show you some results for the second research activity. This is an adaptable porous composite sound absorber. I just proposed some kind of pore network. This is the voids, so we will print obviously the solid part of it, like the solid skeleton. The idea here is that we have a periodic unit cell with a large port inside. It is connected with thick channels and smaller channels, which are skewed with, there are some smaller pores, but maybe the main point is that we have a valve ball inside, and this is made of metal. So you will see that we will use here additive manufacturing technology, but in a very specific way. And these valve balls, they simply block some channels, so they change some parameters like viscous tortuosity, viscous characteristic length, inertial tortuosity, and in that way we may expect to have different absorption depending on the position of the valve balls inside the cells. So this is the periodic skeleton. For one cell we have a array of these cells, and we have such a sample, and you know that we always need to measure, to examine our sample under the microscope in order to update the geometry that we use for calculations to the actual geometry. This is maybe the main slide from the point of view of the manufacturing. I propose that we should first 3D print such a tray tool with which we can take 36 balls at once from the jar, and we can input them into the large pores very quickly. So here you have the sample with the pores, with the valve balls inside the large pores. All the three samples, the sample with the valve balls, without valve balls, and the one without the valve balls, and which is circular, or cylindrical, these are cuboidal. And we measured them in the metal tube with circular cross-section, and we also 3D printed square tube with for these cuboidal samples. And Camille paid a lot of attention to fit it well to our impedance tube. And before measuring the samples, we checked that our square tube is not so bad, because here's the absorption in the metal tube, empty metal tube and empty square tube, and the absorption is sufficiently small. Obviously, theoretically, it should be zero, but there are obviously some losses and leakages involved. And now the transport parameters, which we calculated, that I calculated, it was explained by Camille Perrault during the first presentation, for samples without the valve ball, with valve ball by the propagation in the horizontal direction. And in the vertical direction, we have much higher tortuosity and much smaller viscous permeability and viscous characteristic length. So we may expect these parameters are changed, and we may expect different absorption. Even on the macro scale level, we need to calculate the problem using finite element method, because we have this cuboidal porous domain linked with cylindrical air domain. Here we compute only, do our computations on the quarter of this problem. And you see that close to the interface between the air domain and the porous domain, we have non-planar wave propagation. So we need a finite element method to calculate this problem. And finally, the results for the final results. This is the experimental results for the sample without valve balls. You see that the calculation, the predictions are very similar to the measurements. There's underestimation of the absorption, because in the calculation, everything is idealized very smooth. And now for the sample with the valve ball, but the propagation in the vertical direction, sample is positioned on the in the vertically. The tube is placed on the table in the vertical direction. You see that this is the character of absorption. And now if we hang the sample on the wall, this valve ball blocks the path, the main path, and the airflow is directed into the skew channels, which have smaller diameter than the large channels, the vertical channels, and obviously the tortuosity is also increased. So we move these peaks, the absorption peaks at maybe other frequencies, which were, for example, the frequencies for some kind of noise conditions that we want to adapt to. Okay, so I think that I could manage to finish on time. So these are some concluding remarks, but maybe I will leave them for the discussion if you have some questions. Thank you very much.
Thank you, Thomas.
Thank you for.
Thank you from me too. That's very interesting.
Keith, would you take over and ask for questions?
Yes, okay, I'll do that. So, Thomas, just explain to me again how you change the position of the valve balls. It's simply by the orientation of the sample and the tube.
Yeah, it was done in that way, simply by orientation of the sample in the tube. But if you really want to think about some kind of application, we may think that, for example, it can be done using some not only gravity but with inertial forces. You may have some rotating device and the noise conditions, depending on the velocity of rotation, may be different. And you can use perhaps some acceleration to change, maybe not in this periodic cell, to change the position of the tube. But here we use simply the gravity, but we also think that we could maybe have continuation of this research, because please remember that the valve ball is, the bearing ball is made of steel. So, okay, it's pretty heavy, therefore it clogs the channels very well, but we can also use maybe magnetic field to play with it a little bit. It will be at least publishable, maybe not very efficient, but I think it will be publishable if we want to continue with this. But for this, right now we just use gravity.
Very good. More questions, please.
If I may, it's Philippe Leclerc from France. If I may I ask a question to Thomas?
Yes, please. Salut, Philippe. Yes, please. You can ask a question.
Thank you. Thomas, you mentioned some results on UTC samples on in the round-robin test.
Very interesting. Yeah.
Do you remember? Maybe there is someone from UTC here, but do you remember the solution they had in order to have better results with less discrepancy? You mentioned they impregnated the sample with something, but what was their solution?
Yes, I remember. I think that I'm sure I put in the paper. I will send you the paper. Maybe I will wait. Okay, I will send you the info, maybe not the paper because it's under review right now and I don't want to distribute it before. But I will send you any information about the solution that they used to impregnate the sample, because Nicolas Daucher sent me all the data. And I will also send you some data concerning the grain size, because this is actually very interesting. We will have some continuation of this collaboration concerning this samples made from polymer powder, because we really have this effect of microporosity here, and we know very well the let's say mesoporosity geometry. So there will be a lot of modeling involved, double porosity model, and we will try to compare modeling with these results. But basically, it was like that. They simply impregnated the samples, and suddenly they got the same results as for the resin samples and for my samples. So we are sure that this is microporosity. This is evident.
All right, thank you very much. Because I was asking because we had a similar problem, I think.
I will send you. You can also ask directly Nicolas Daucher, but I will send you the data concerning the grain size and the solution, the chemicals solution that the compound that they use to close these micropores, because I have them in the.
All right, thank you.
You're welcome.
So Kirill, I see someone's asking about getting hold of the presentation, but presumably they're available through UKAN because they're on a UKAN site.
Well, we going to share a common folder with everybody through the UKAN website, which contains not only presentations presented today, but also for all the webinars which UK Acoustics Network run. So this will be available by going to Acoustics AC UK resources. You'll find it over there. Alternatively, I'm happy to share also this link with you when Olga becomes available, because she knows all your email addresses.
I see there's a typed question for Thomas from Zoe, whoever Zoe is. Zoe is asking, were the balls inserted after printing of each layer? This is back to the valve balls.
Oh yeah, they're a very good question. I was very quick with this presentation, so I couldn't explain it. I hope you still can see my my screen, the slide. So it was like that we put some you can put in the code for your 3D printer, you can put, for example, some technological breaks. So at each level, and there were 12 levels, we put a technological break. So the printer was terminated. I mean, it was stopped at each level, so we could insert the valve balls into the large balls using this tray device. And we did it very quickly, and then we just need to press the button to restart the 3D printing process. So it was done in that way.
We probably need to finish this now, Kees, because we're running a little bit late, not too much late, and it would be nice to pass to the next speaker. I just want to say we've got 65 people signed in now, and I just sent you the link to the folder which contains the copies of presentation. I also will put a link to the video from this webinar in this folder when it becomes available. Okay.
So I'm switching my microphone right now.
And can you switch off your presentation, please?
Okay.
Yeah, just cancel your screen sharing. And we pass it on to Philippe Leclerc. It's in the top right corner. It should be a green icon, so which you can say it's screen. You should click it. That's it. Yeah. Philippe Leclerc.
Hi. Thank you very much. Well, thank you, Kirill, and thank you, Keith, for inviting us to give a presentation. So I will share my screen too, if I do it properly. Okay.
Sorry, before you start, Philip, I just remind you that there is a list of the speakers particularly, so there is a list of questions in the chat, which the presenters may look at and then respond either online or subsequently.
All right. Yeah. So okay. Sorry about that. I didn't know how it worked. Can you see my presentation now? Or
yes. Can you make it full screen, please, Philip?
Yeah. Okay. So my presentation will be on pancake absorber, and probably the geometry will illustrate the difficulties encountered in 3D printing, because we had to create these samples, and we also had some problem in making them, but we don't have the experience of Thomas, of course. So this work is a teamwork between a UK team, a French team, and also now a Canadian team, because Thomas Dupont is now in Canada. Okay, so the outline is, well, I will talk about pancake absorber, but before that, I will try to explain the origin of this design and how do we come to this idea by talking about dead end pores. And then I'll give some results on the performances of our absorber, and especially in under high sound pressure level, which was a subject we wanted to study. And lastly, and this is probably related to the previous presentation by Thomas, the problems we have encountered in trying to 3D print these samples. Perhaps we'll have a solution at the end of this workshop. So the pancake absorber, how do we come to this idea? Well, we had some experience in the study of porous materials, and we noticed that perforated materials, which is a particular porous material, bearing lateral quarter wavelength cavities like this, and distributed periodically on along the main perforation, was giving very interesting results on the low frequency sound absorption of this kind of sample. So we set out to study theoretically and experimentally if it was possible this kind of structure. And for the theoretical part, we thought to model this, of course, as a single perforation with periodically spaced lateral cavities, but also we had to account for the fact that we could have several at a given node. This could be called a node. We could have several cavities at a given node, and so we tried to model the structure. In the modeling, we ended up with the dispersion equation, which is quite simple, while the resolution of this equation is not that simple, but the equation itself is all right. The important parameters in this is, well, H is the periodicity, K is the wave number in the main pore, and Q is the wave number in the effective fluid that represents this structure or its rigid frame. But one important parameter is this X, which represents a non-dimensional admittance. It looks like it. And in this parameter, you have N, the number of dead ends per node, A, the cross section of one dead end, AMP, the cross section of the main pore, and the surface impedance at the entry of any dead end here. And this parameter is very important for future designs of materials. So we did a simulation with typical values. You had the typical values here. So with these values, we could see that the Bragg frequency, which is related to the periodicity of the structure, is 17K hertz, which is a bit too high compared to what we expected and what we observed. But also, surprisingly, in the dispersion curves, we noticed that there are 2 low frequency peaks predicted in this example, and which are absolutely not related to the Bragg frequency, but which is related to periodicity. So we have other effects, and we try to understand this because this was a very interesting, surprising, but also very interesting result for low frequency applications. So as remarks for this first presentation is we had two interesting important remarks. First, ducts with lateral cavities periodically spaced are not new, but here what's different is that the sizes, everything is millimetric or submillimetric, and this is quite original. Well, it was original in 2015 when we studied this, and so that the total thickness of the sample is only a few centimeters, and we can see that we will see that there are some interest at very low frequency. So the originality in this study is that the suspected effect is the viscous thermal effects, which are accounted for in this structure at millimetric or submillimetric sizes, and these viscothermal effects result in a wave slowing effect. So if you reduce the sound speed in the structure, you will reduce the resonance frequency. This is a resonator which will be used in absorber, but you reduce the resonance frequency. So this is the physical effect behind this design. A bit more detail on the model, on the analytical model, because this will lead us to very simple design formulae. So we have this structure. We have a unit cell that so you can stack several of these unit periods to create the material. So everything here in the model basically is modeled as a simple perforation without dead ends, but with equivalent properties. So wave number, sorry, I have to get rid of we have a wave number, and in the model we found that at very low frequency and in the situation where we have short dead ends compared to the wavelength, so the dead ends are not too long, then we have a very simple low frequency expansion of the result of the theoretical dispersion curve, and which shows that the effective density of the fluid in the equivalent fluid is that of the main pore without dead end. So the effective density of the fluid with dead ends is the same as the density of the main pore without, which has some importance, because as we will see in our model, we have a tortuosity of 1, which is different from what probably Keith will present. But in our study, the important result is on the fluid compressibility, the air compressibility. The equivalent compressibility is given by that of the main pore without dead ends, plus the contribution of the periodically distributed dead end pores. And this last formula will provide us very interesting analytical formula that will help us to design the material. In effect, what is happening when the wave propagates? We can see from the equation that tortuosity doesn't play a big role, but here what's happening is that we will have thermal exchanges between the air inside the dead ends and the air in the main pore, which is illustrated by this modification of the compressibility of air compared to that of the main pore due to the effect of dead ends here. So what do we want from this formula? We want, in fact, we want to increase the compressibility, because if we increase compressibility, we will reduce sound speed, and then this will reduce the resonance frequency. And with this formula, there's not much we can do on the main pore compressibility, because it depends on the sizes of on the diameter of the main pore. Actually, this is one of the parameters that Camille presented, one of the Johnson-Shampoo-Alas parameters. But we can play on the dead ends. So if we look at this expression, we need to increase the number. If we increase n, it's good. We need to increase the number of dead ends per node. We also need to increase the cross section of the dead ends and reduce the cross section of the main pore. But these two conditions are difficult to realize, because it's to implement, because we cannot control much these. We can also decrease the periodicity, which is good for us, because it will contribute in reducing the thickness. And last, we can increase the length of the dead ends, but also we are limited because the lateral, we need to keep a good perforation rate. So in this design, one thing that is very easy to do is to increase the number of dead ends per node. And we can have, for example, 4, then 8, and 16, and so on. But in the end, we thought, why not create an entire cavity instead of multiple dead ends? So this is what we did. And we ended up with pancakes. And we think that these provide the best results in extension of this design. And furthermore, it's also obvious that these are slightly easier to design as this, so everything is good for us. So we went for this design and studied it numerically, analytically, and also experimentally. And here are a few results provided, some interesting results. What is important is the thickness of the samples, resulting in the design of the multi-pancake design with the central perforation here. And the resonance frequencies are quite interesting because they are quite very low for the given thickness. And the model, the analytical model is based here on double porosity, one corresponding to the porosity of the pancakes and one corresponding to the porosity of the main pore. Another example for larger thickness, which is of course improves the performance at low frequency. We were also very much interested in the behavior of these materials under high sound pressure levels, and we started to think about modeling this behavior. And the idea that came out, we had some experience on that already in the past, so we tried to apply it here. The idea was to give a modification of the flow resistivity of the Darcy's law flow resistivity using a high flow velocity Four-Kammer nonlinear parameter. So it's a modification of Darcy's law, including the Four-Kammer nonlinear parameter. And if we integrate this inside the analytical model, we have an analytical model providing behavior with sound pressure level, input sound pressure level. And we can see that the pancake absorption peaks, they reduce with increasing pressure. We could try to test experimentally and compare with the theoretical results. So considering only the first absorption peak, which for now is the main peak of interest for us, we plotted the variation of absorption coefficient of this peak with incident sound pressure, and we could find a fairly good match between experimental data, which are given by the dots, and the main curve, the theoretical curve. Now I'll finish my presentation on some problems we encountered with 3D printing. So we're very much in need of trying to have ideas to improve the manufacturing. To illustrate this, I will present this design of the pancake absorber, but with a profiled central perforation. What's the idea behind this? The idea is first to increase the perforation rate at the entry, also to exploit this wave slowing effect by slowing even more the wave, using a design that is already known in by people doing black hole effects in acoustics. So here we try to combine the acoustic black hole effect with profile central perforation with the pancake design, and this is what we get. So we have an analytical model for this, but at the time we studied this, we didn't. So we used the FEM model at that time. And but in doing comparison between theoretical and experimental results, we observed some strong discrepancies. And actually, we already observed this in the past on other samples, these discrepancies, and we knew that it was a microporosity effect. We observed discrepancies in sintered, the 3D printing, but with using sintering technology. And of course, in this technology, we probably get microporosity. And here it's slightly different technology, but it's still, we can observe that we have some surface roughness and probably microporosity. And so this resulted in strong discrepancies in the prediction of the resonance frequencies and also on the values of the absorption peak. As already shown by Thomas. And here is the result of simulation compared to experimental results in green, but accounting for some microporosity effects here. But here, of course, it's difficult to correctly predict the experimental curve because we have at the moment we don't have a clear idea of the about the properties of the microporosity. So, but this simulation was just to show that with accounting for microporosity, it was possible to have a much better match between experimental and theoretical results. And so to conclude, the main problem we're facing at the moment is is one of the main problems. We have some interesting modeling, some interesting design, but one weak point at the moment is how to make the sample, to build them. And in the past, we used several technologies like plate stacking. So if you have a series of plates and you alternate this design with this, you can create the pancake structure you need. This is an example of a handmade one by simply cutting and using washers, or we use rings, and also we stack things. Here is an example of 3D printed sample, not made by us, but by a company. And the technology was all right here because they use, I think they use 3D stereolithography, 3D printing. And here it is clear when you look at the sample that you don't have these problems with microporosity. So in this case, the match between theoretical and experimental results was all right. And we're also facing at the moment with 3D printing some other problems related to the building itself of the material. If you make the material from bottom to top, the floor is very easy. You just make a plate by 3D printing. But how do you create the ceilings without it falling? You see that the problems. So it seemed when they did 3D stereolithography printing, the they overcame this problem. But this is something that poses problems in the design, well, not design, in the making of the 3D printing sample. So I hope in the discussion could be very interesting ideas to make this sample. So I'm pretty much finished. So I thank you very much for your attention. And if you have a question.
Thanks, Philippe.
Yes, okay, thank you.
It's very good turnout. 68 people now in attendance of this seminar.
Yeah. Okay, so I think Thomas will have a lot to say about the 3D printing process. But after Thomas has finished saying what he wants to say, I have a question too.
Okay, so I believe that I can ask Philippe, because you said that they 3D printed this sample using resin-based stereolithography. And a comment to this is that when you use different technologies, you must be very careful, because some of them, they require treatment. For example, when you use stereolithography, you don't have problems with microporosity, but you may have problem with the resin. And you need to get the resin out of these, let's say, small slits, for example, in your cake, between the pancakes. And there's also a problem with curing using ultraviolet light. So this problem, this can be very problematic. For example, Camille, my PhD student, we are doing some research together with Keith on micro slit absorbers, and we tried to use stereolithography for that, and the resin inside the slits was actually remaining there, and we eventually used the very good FDM printer to manufacture this. But if you 3D print your samples in that way, that maybe you print parts of these samples and join them together, it is possible. Another thing, I'm not sure if you mentioned, if you have mentioned that, but you must always update your microgeometry. So if you have a design that you use for some initial calculations, then after 3D printing, you must check the, let's say, diameters, slits, and so on, and update your geometry for your calculations. I'm not sure if you did it. So this could be also a very important, actually, reason for the discrepancies, because I was a little bit astonished that you got higher absorption in your predictions than in the measurements. Do you know what was the reason for that?
I'd like to say something about that if before Philippe answers. Sorry, Philippe. Don't you think it's rather interesting that in your absorber, based on improving compressibility or modifying compressibility, surface roughness and microporosity actually reduce your performance, whereas in the designs that Thomas was working on, actually microporosity, at least I don't remember about surface roughness, improved the absorption performance.
Yeah.
Yes, you're right. Actually, we already faced this problem in the past, in 2015, and the result was that indeed the microporosity and surface roughness was improving the absorption, and also slightly reducing, if I recall correctly, slightly decreasing the frequency, which is good. But yes, in this simulation, maybe we could maybe well, I just remind that in the simulation we have absolutely no idea, and we tried in the FEM modeling to fit some parameter just to show that we could achieve a better fit. But of course, since we have absolutely no idea on microporosity or surface roughness, we cannot speak with you know with we cannot be sure of the simulation itself. But you can also see in the curve, I think, that the general trend is that if the frequency decreases, the quality factor seems to increase, which is well, to me it looks like a normal behavior, like something that's fairly common. But maybe, well, surely you're right on the theoretical results obtained by FEM modeling. It's clear that the absorption peaks are lower frequency and higher, but they're also narrower. So yeah, it's what I want to say on this simulation. It's that here we're not sure of anything, and we were just trying to find some better match by simply, you know, playing with the FEM code and try to see. And we just showed in this curves that it was possible. But of course, these results shown in the last slide on my presentation are not accurate, and then they're just here to illustrate the possibility that we can improve the modeling by accounting for microporosity and surface roughness. Yes.
So shall we give you a chance to have a cup of coffee?
Yeah, I think so. I think a 5-minute break, okay. And people can type in questions which can be answered later, perhaps.
Mm-hmm. Yeah.
70 people so far signed in, which is very impressive.
Kirill, so are we going to meet in 5 minutes? What time are we going? 5 minutes, okay.
11 o'clock. Shall we meet at 11 o'clock?
Well, we yeah, just make a cup of coffee and come back again so we can have informal chat. We will start 11 o'clock sharp.
Okay.
That's 12 o'clock US, UK.
11 o'clock UK time. So it's
11 o'clock UK time, 12 European time. Okay. Philip, can you stop sharing your screen, please?
Yeah, I was just trying to.
It's must be in the top right corner, little round icons say screen.
No, but sorry, I'll do it. I'll do it anyway. So it's coffee break, but I'll before that. No. Okay, it's done.
Good man. Okay, I'll see you soon.
Okay. Yeah.
Keith.
Yes, hi, Kirill.
Yes. Shall we get Jean to share the screen?
Yes, please. He did have it shared, I think, before the break.
Okay.
Yes. Do you see it?
Yes. All good. Are you all ready, guys?
Yep.
Well, in this case, hopefully you refill your coffee and teacups or whatever else you're drinking this time of day. And shall we give the floor to Jean?
Yes,
So
please.
I can start?
Yes, please.
Okay, so hello everyone. I am Jean Boulevert and I will give this presentation with Valerie. We are from Le Mans Université, Polytechnique Montréal, and Safran Aircraft Engines, and we'll talk about the defects coming from additive manufacturing of printed porous materials, how to deal with these defects in the simulations in order to obtain reliable results. And finally, we'll present some result of optimizations of these materials having a gradient of properties. So let's start with the defects coming from additive manufacturing. So from what we see in the literature and also from what was discussed this morning, for a lot, I would even say for all additive manufacturing techniques, for say SLA, JMP, FDM, and so on, when you print a porous material at the end, the material you obtain is not the one that you had in mind when starting your project. And so, for instance, from this paper, it is said that there are roughness and imperfections on the foam that is printed. Second paper, well, the pore diameter is not exactly the one that was expected. And third paper, the filaments are not cylindrical as expected, but ends up to be ovoid. So we see in the literature that the porous material are not exactly as they are supposed to be once they are 3D printed. And what is the impact of the defect on the behavior of the porous material? Well, it tends to increase the losses of the material, of the intrinsic losses of the material. And in terms of absorption coefficient, for instance, we see that there is an underestimation of the measured absorption coefficient in comparison to what was predicted. So, for instance, here there is a 0.15 absorption coefficient decay.
Okay, I will now cover some problems related to defects and anisotropy. So we've been talking a bit about anisotropy this morning. I think Cami involved it in the homogenization process, and also Thomas with the valve ball, which actually is kind of a selective anisotropy. You can imagine this very simple unit cell, which has different size poles on the different directions. And we tried to actually print those samples. And from on the left side picture, the picture on the left side, what you actually see seems pretty much the same as of the idealized unit cell. But in fact, when you look closer with a standing electron microscope, for example, you will see corrugations that appear. And basically what it does is that it induces anisotropy in the porous layer, because you have this layer by layer surface roughness, which actually increases the fluid solid interface, but it's also direction wise. So yeah, you have those two anisotropic properties. One is purely related to the design of your unit cell and the choice of it, and the other one is purely linked to the inherent defects of the additive manufacturing technique.
So now that we have seen that there are defects on porous materials that are 3D printed, let's see how we could deal with them. So let's start with an example of porous material that is an open cell fibrous porous material this one. So it's we call it a microlattice. So it's just composed of parallel fibers. So here is an idealized representation of this material. What is nice with this material is that it can be simply 3D printed, and that just by changing the lattice constant, so here it's the C distance, so the distance between the filaments, you can actually tune the properties of the material. So it's a simple material that we can easily 3D print, and also that we can easily simulate. So it's the theory that has been presented before this morning. So you can numerically predict the intrinsic parameters of such material. So we 3D printed this material using fuse deposition modeling technique. So a very simple method where you extrude a melted filament and place them on top of each other. So it really suits to the printing of such material. And again, with this technique, you can easily tune the lattice constant of the material, so the distance between the filament, by changing one parameter that we call here the infill factor. So here you see for two different infill factors, the resulting microlattice. For those who are more used to felts, the common felts, changing the infill factor will correspond to changing the compaction rate of the film.
Okay, I will now cover the defects that actually occur during the 3D printing of such microlattice. So the first one is basically when the nozzle, during the deposition, basically, since the nozzle is connected to the previous layer that has been printed, the deposition is actually constrained. So the cross-section area of the filament is not going to be perfectly circular, but rather slightly elliptical. This is pretty well observed during all of this FDM process, but you cannot actually consider a perfectly cylindrical cross-section area. Another effect that appears is during the deposition, you basically have a stretching phenomena as seen on the pictures, orange pictures. Basically, the cross-section area is being reduced because of the stretching and the stretching phenomena that occurs in the direction of the nozzle displacement. So this is the second type of defect that occurs. And also, since the nozzle is not a perfectly circular shape, you have those, I would say, micro corrugation and defects that are present originally on the manufacturing of the nozzle itself. And those induces micro grooves, like small perturbations on the circumference of the filament. And this is actually the third defect that can be occurring during the manufacturing process. But what we can do is actually try not to idealize perfectly cylindrical rods, but since we now have SEM imaging techniques, you can do like the reverse engineering process and try to homogenize by finite elements these cells with the defects, like correcting the cross-section area and also accounting for the small perturbations on the edges of the filaments.
So exactly, to account for these defects, either you can change the unit cell to account for them, or what you can do is directly do the work experimentally. So we can use inverse acoustic characterization to retrieve the intrinsic acoustic parameters of an homogeneous sample. So basically, you put an homogeneous sample in an impedance tube, and with some method, you can come back to the acoustic intrinsic parameters. So in this way, you can obtain the acoustic parameters of the microlattice for different lattice constants. So what we did is that first we computed for from the idealized unit cell the variation of its acoustic intrinsic parameters for porosity, tortuosity, and so on, with respect to the infill factor, so with respect to the lattice constant. So we computed them from the idealized unit cell, so here are the blue lines, Then we set some inverse characterization bounds, so the green lines. And these bounds were set accounting from the numerical results of the defects. So for instance, simulating the defects, we saw that the viscous length tends to decrease when considering the defects. So we said, okay, during the inverse characterization, the viscous length that we'll get from experimental measurement must be lower than the one from the idealized unit cell. Then, so we perform the inverse characterization on, I think, 8 homogeneous samples having different infill factor. And finally, we perform some monotonic interpolation of the data. In this way, we can obtain the variation of the intrinsic acoustic parameters of our microlattice in function of the infill factor. And what is nice with these results is that experimentally, we see that, for instance, the porosity is higher than numerically, and that it is what was predicted by the simulation of the defects. So we can get the acoustic parameters, and they are coherent from what we expected from the simulation of the defects.
Okay, so we will now talk about optimization of graded media. So what you have seen so far was purely homogeneous medium, and now we will gonna show you different approaches to actually model graded properties using the geometrical gradients. So just a quick overview of the propagation and optimization methods that we have been using during the past years. So for the propagation, we have very common techniques such as the transfer matrix method, which has a very low computation time and is has an analytical derivation. We also have been working with a Pano series and also wave splitting techniques, which require higher computational time, but may give you insight on the losses inside of the material. So this is mainly for propagation techniques, which allows us to predict the absorption and reflection properties of graded medium. And regarding the optimization, what we do is set different cost functions for example, to cover frequency and angular ranges, and they are defined also relative to absorption, reflection, or even impedance that are going to be minimized. Those graded properties can then be modeled by different manners. You can, for example, try to optimize the geometrical parameters for different layers, successive layers. But depending on your discretization, you may have to optimize for very, very large dimensions, but you can reduce those dimensions using interpolated polynomials and so on. And overall, the whole optimization technique is done using the Nelder-Mead algorithm, which is well known, which is going to minimize actually the cost functions. It inputs a random geometry, a random initial condition for the material, because it may get stuck in local minimum. So we try to do as much draws as possible in order to have the best cases for absorption objectives, I mean.
So now let's speak about one example. So this one is in normal incidence. So what we want to do is optimize the gradient of properties through the thickness of the material. So the property here is still the infill factor of the microlattice in order to have a perfect absorption in a targeted frequency range. So we start with the homogeneous material, which has this black absorption curve. And we say that we want in this frequency range to have the highest absorption coefficient possible. So by means of the tools that Theo presented, we can optimize the gradient of infill factor through the thickness. So it takes this shape. Numerically, we are supposed to obtain the blue curve of absorption. So, okay, then we 3D print the corresponding sample. We put it in an impedance tube. We measure its absorption coefficient, and what we get is the red absorption curve. So what is nice here is that, okay, we can optimize the gradient of properties of a material numerically, but what is even nicer is as we considered the manufacturing defects their impact on the acoustic intrinsic parameters. Once we 3D print the sample that is optimized with a gradient of properties, while its absorption curve is the one that was predicted.
One more thing we can cover with these optimization techniques. So if you remember, so on the top left corner, you have the previous unit cell that I presented in the beginning, which is pretty simple to design actually, and to introduce anisotropic properties. So you can control the geometry of this unit cell by the stretching factor, which I denoted T1 and T2, which give you a simple anisotropic tuning. And basically what you can do is, instead of considering only the normal incidence, you can have, for example, on the top right corner, 400 incidences, which are gonna impact a finite layer thickness, which is actually infinite in all the dimensions. And we can optimize the average absorption and diffuse field absorption coefficient with the same optimization techniques, but this time considering anisotropic properties and graded properties in the material. So what we see now on the bottom left corner is, so the dashed black line is the homogenized, is the optimized homogeneous material between 1 and 5 kilohertz for all of these incidences. So we see we only have one pitch of absorption in this 1 to 5 kilohertz range. So this is actually for 25 millimeter sample. And when we grade the properties and allow them to be anisotropic, what we can do is bring back another maximum of absorption in this frequency range, which allows us to actually maximize the absorption on the whole frequency range, because the second zero has been brought back in this frequency, in this optimized frequency range. So you can see on the right the geometric profiles. So the porosity is varying. Of course, the size of the pore tends to be very small. And we also have this factor G, which shows the anisotropic properties. So basically the stretching of the unit cell may be graded across the depth of the layer. And this is also something you can do with the microlattice, because it has anisotropic properties depending on the direction. When you look at it, we have these cross patterns that are, of course, different depending on the direction. So anisotropic cells and their geometric properties can be adapted and optimized for normal incidence and also diffuse field acoustic properties.
So to conclude, we have seen that if you just consider an idealized unit cell of your porous medium, you will obtain a prediction of its acoustic behavior that is correct, but not very precise. Because when you 3D print this material, the unit cell changes because there are some additive manufacturing inherent defects, and these changes of the microstructure impact the acoustic behavior of your material. And also, what we didn't say, but it's quite important, is that the manufacturing defects, well, they depend on the process. If you use plastic or metal or different techniques, you will not have the same defects, but you are likely to always have some defects. But these defects are only a problem if you cannot take them into account in your simulation at the end. Because what we have seen is that we can consider them numerically by changing the unit cell considered in the numerical simulation, or experimentally using some inverse characterization of homogeneous sample. And at the end, you get a parametric model of the intrinsic parameters of the homogeneous material, and that is reliable, that corresponds to the experimental data. And of course, you can use them for optimization purpose of gradient of properties, for instance, or many other applications you are free to use.
Regarding now the perspective that we are going to look for in basically what you can do is also try to print unit cell with very high aspect ratio in order to control these anisotropic properties. So this is something we look into. We, regarding the defects, are going to also work more on the imaging techniques. So as Chami said this morning, we can use scanning electron microscopy and computed tomography in order to actually go deeper inside of the structure itself and see if we have a great repeatability and periodicity inside of the layer, and also account for the I mean, to actually quantify the defects that have been printed. And also we can optimize the transverse properties for optimization of sound absorption in line depths. That's pretty much it. Also, we have a few references that will be available to you on the slides. And if you have any further questions, feel free to send us an email or to ask questions. Thank you very much.
Thank you.
Perfect timing.
Yeah, of course. 20 minutes.
And good teamwork as well, guys.
Thank you very much.
Teamwork.
Yes,
may I have a question?
Yeah, who is that?
Thomas.
Yep.
Go ahead, Thomas.
Very nice presentation, by the way. I have a few comments and one question, maybe, or maybe one controversial comment, so you can discuss this comment. First of all, I would like to say that the first reference, it was actually my work for a conference. It was not SLA but FDM technology. So and it was actually not updated, and there were windows, not cylindrical channels linking the pores, so there was a lot of roughness involved. Regarding the micro grooves and all this kind of roughness, so obviously we need to take it into account, and perhaps Camille Perrault will correct me, but there are works like by Cortis and et al. Which may introduce some kind of roughness on the surface in order to increase the viscous effects regarding the dissipation of acoustic waves. However, there are also, sometimes we may look what is really the reason for the discrepancies between the measurements and the absorption. And for example, I know that John Kennedy from TC Dublin, who was involved in our round robin study, he also does the modeling and calculations, and he maybe it is a little bit controversial approach, but to fit his curves, he artificially increased the viscosity of air. And then he claimed, okay, that this is really roughness and viscosity which is responsible for the discrepancies. Another comment, which is also a little bit obvious, we should obviously compare and maybe directly measure the effective bulk modulus and density, which is possible right now. For example, people from Matalis, they develop this kind of improvements for your impedance tubes that you can use, and to measure these complex curves directly and compare the real and imaginary part. And the final comment, which is actually maybe not so obvious and maybe not true, so I'll put it under discussion. We also need to seek to look for the discrepancies not only on the side of measure on the, let's say, fabrication, but also and the thing that we do not model in that way. But perhaps it is like that sometimes we usually print the pores which are larger than perhaps we want them to, and because of that we may have some compressibility of air inside the pores, even if they are not closed, they are not Helmholtz resonators, they are fully open from different sides. We may have compressibility involved here. And please remember that in the theory that was explained this morning by Camille, on the microscale level, we assume that the flow is incompressible, so we can uncouple the thermal effects from the viscous ones. But I'm not sure if this is really the case, and when it is really important, what the size of pores must be to get this effect. But still, we can play also using this effect. So this is a comment maybe that should be discussed as well. Thank you.
Thank you.
Jean and Theo, do you want to respond to that?
Yeah,
there were many points. Well, one thing is about the rugosity. and changing the properties of air. But what I would say, what we have seen from the simulation and experimental data, is that it mostly impacts the viscous and thermal lengths. That is normal, because if you look at the definition of the characteristic lengths, they depend on the ratio of the surface divided by the volume of the unit cell, the surface between the air and the solid structure. And if you have viscosity on the surface, then it's the surface of the fibers will increase. So it's normal that the lenses will decrease. So, and yeah, was just a comment.
Yeah, I wanted also to comment on that, as what Thomas has said regarding the viscous effects. So yeah, basically what we have been seeing from the homogenizations by finite elements that we have been conducting is that when you change, I mean, those microscopic defects actually completely change the fluid solid interface. And as Jean has said, since the thermal and viscous characteristic length are purely based on the ratio of the fluid solid interface and the fluid volume, you will basically, you can actually change the thermal and viscous lengths by a factor of 2 if you have those ruggosities on your filaments, for example. So yeah, the printing defects here have a very, very strong impact on the length. And also one other one that you pointed, Thomas, regarding the characterization. We, if I'm not mistaken, we actually do the retrieval of complex density and bulk modulus using 4 microphone techniques. And what is also done, actually the impedance tube is here using 2 microphones. But what we do for the inverse characterization of the acoustic properties and transport parameters is using Bayesian techniques in order to fit the, I would say, corrected JCIL parameters. I don't know. Yeah.
Can I say something, please?
Yeah.
I think I have a technical point and then I have a commercial point. Okay, so the technical point is that we should catalogue the defects that improve the absorption, because at the moment you're allowing for them accidentally. But what about the possibility of introducing them deliberately? So that's my technical point. And the second point is Safran aircraft engines are interested in your work. Is that because they can foresee 3D printing of aircraft engine linings?
Okay, so maybe I can answer for the first point. In my opinion, the defects are not, well, they can have a good or bad impact, but from what we've seen in the microlattice, the defect is not good or bad. Let's say it just has a certain impact that I would say it increases the losses of the material. So usually when you don't have enough losses in your material, for instance, as these 2 samples, when you increase the intrinsic losses, you will have a higher absorption coefficient. That people will say, well, it's good to have a higher absorption coefficient. But in the opposite, if you are supposed to have a perfect absorption coefficient and you increase again the losses, then it will, the absorption coefficient of your material will be lower than predicted. So from this point of view, the increase of losses due to the defects are not good or bad. They are just what they are. And yeah, but also I also agree that some defects could be nice, for instance, by decreasing the absorption peak towards low frequencies and so on. But for what regards the increase of intrinsic losses, I would say it's not good or bad.
Yeah, I will join you, Keith, on this point. Yeah, that's why I think we also will focus more on imaging techniques, because the better we will know those defects, the better we will be able to take advantage of them and possibly increase or at least enhance the acoustical properties of all materials because we still see them as defects, but they are just inherent properties of the printing. And yeah, regarding Safran aircraft engines, they are the main funding for this. I mean, we're still doing a PhD, Jean and I, and they are the main funding on these additive manufacturing techniques.
But is that because they can foresee being able to use your optimized 3D printing in
I guess,
practice?
yeah.
Okay. Interesting.
Other questions, or maybe we are out of time. I think Luke's next speaker.
I think I'm the next speaker, so I better get ready.
Right.
So I stop sharing my screen?
Yes, please.
Thank you very much.
Yeah, thank you. And thank you for the questions.
In your own time, Kiss.
Those are my grandchildren.
Lovely.
Now I've got to find the presentation. Okay, so are you all ready?
Yes, please.
So I think we've heard some very interesting things about what can be done by designing a microstructure from scratch to do a good sound absorbing job. And to some extent, I think this work has been anticipated by people who are interested in micro perforated sheets, because they've not had the distraction of trying to explain the absorbing properties of bulk manufactured materials. Basically, they are artificially manufacturing everything. And so they've been able to go into detail on what they can achieve by changing the shapes of slits and perforations and their density and the looking at end corrections and all this kind of thing. So I think to some extent, people interested in bulk absorption are maybe a little bit behind. So I'm going to talk about what might be achievable using simple pore structures, and particularly ones for which analytical models are available, because if eventually you get into an optimization process, then clearly it's going to be numerically and computationally much more efficient if you use analytical models. So I'll talk about what you can achieve with identical inclined pores, and then non-uniform pores, and then intersecting pores, and then partitions. And I may or may not talk about the associated metamaterial effects, but then some conclusions. So it's well known from steady flow considerations since the time of Carman's book, P.C. Carman's book on flow through porous media. I've forgotten what date that is. It might have been the 1930s.
It was 1930s.
Thank you. That the pore shape can influence the bulk flow resistivity or permeability. And since that time, people have worked out lots of things for lots of different pore shapes, or at least 4 shown here. But other people, I think there's been work on hexagonal ones and annular ones. And anyway, the important thing is here that if you can take a certain dimension value of B or A or D, then the shape that's always going to give you the highest flow resistivity for that given dimension is going to be the cylindrical. Actually, I won't talk very much about cylindrical ones. I'll talk mainly about slit ones, which in principle are the least advantageous from the flow resistivity point of view, but they're also relatively simple to model, and my computer doesn't like doing complex special functions. Something that's been known since, I think, 1949 or perhaps earlier time of Zwicker and Coston is if you angle the pores, incline the pores with respect to the surface, then you increase the tortuosity. And what I'm talking about really are going to be all the microstructures that can help increase the tortuosity, because if you're looking at a thin layer of material, that's a very important parameter to try and increase in terms of shifting the first layer resonance to a lower frequency. By the way, that also relates to slowing the sound speed within the material in a different way to the way that Philippe discussed. So you can see immediately for these particular set of parameters how going from normal to the surface to 45 degrees to the surface to 70 degrees to the surface, you shift that low frequency peak absorption. Ten years ago now, Fabien Cheviot and co-workers looked at perforated metallic foams. So these are fused metal spheres which you then perforate and you create pore structures like the ones shown. And they developed a very nice theory for deducing the parameters you need for the Johnson-Champoux-Allard model. For predicting the properties of that perforated foam, in fact, it turned out that the measurements were a bit different from those predictions because they had a perforated facing as well. And when they allowed for the facing, they got better agreement. But let's just look at what you can do in terms of getting an equivalent result for the non-perforated facing situation by just using inclined pores and inclined slits. And with those parameters, you can actually reproduce that perforated metallic foam. So here is a very simple microstructure that's giving you the same kind of absorption coefficient as you might get from a bulk manufactured material with a much more complicated microstructure. So again, we go back in time to Champoux and Stinson, who went to the trouble of actually creating a material with non-uniform pores. I've forgotten now what materials they were using, but maybe latex, rubber tubing, and some kind of other way of getting increased.
I think they cut grooves in Perspex case.
Oh, Perspex, right, okay. And essentially they found that even when you had pores normal to the surface, this increases the tortuosity inside the material, and therefore you change the acoustical properties. And they were able to, because they knew precisely what material they created and the characteristic dimensions inside it, they were able to predict what it should do in terms of the real and imaginary parts of impedance and the real and imaginary parts of propagation constant, and that fitted pretty well with the measurements they got. So this is, if you deliberately create non-uniform pores, you can change the acoustical properties of a thin layer. So I've looked at, I mean, they had created cylindrical pores and non-uniform cylindrical pores. So I've looked at a much simpler example where you create non-uniform slits. And I've looked at what the tortuosity, how the tortuosity would vary for this very simple system according to the parameters in the system. And not surprisingly, it turns out that within the range of parameters I've looked at, then if you have equal lengths for your different cross sections, then that gives you the highest tortuosity. So also, I haven't given the reference here. There's a paper by somebody whose name I can't remember, who looked at sinusoidally non-uniform slits as well. So I've compared this particular rectangular non-uniform slit, the absorption coefficient that would result from that, from having a lot of these, to what would happen if you had the sinusoidally non-uniform slit with these parameters. And you can see that compared with the original uniform slits, you can change what's going on. If you like, this is a kind of artificial roughness, hence all my questions about what happens if you deliberately make use of some of the defects you're finding due to roughness or rugosity, as the French like to call it, in the pores. So I think you could set out to deliberately create non-uniform pores in order to get a target absorption performance. There's another paper. I mean, all of these ideas basically have not yet been validated. Sorry, that I'm going to talk about one piece of validation that's occurred as a result of collaboration with Thomas, for which I'm very grateful. But anyway, here's another idea. Basically, what you have is you have intersecting slits. So this is a kind of inverse of the lattice arrangement that Jean Bouvard and Theo Cavaliera were looking at, and this can also affect the performance. The people who published this original letter were interested in seeing what you could do in terms of the absorption of an incredibly thin, well, relatively thin layer, only 1 centimeter thick. So this shows you how the absorption can be remarkably changed compared with having identical pores. They also did some FEM analysis, and here I'm showing one of the plots that they got, which is quite interesting, and it shows that there are things that could be investigated even further that are going on at the junctions between the micro slits and the meso slits. In fact, the analytical results that I showed before, how do I go back? Yes, these analytical results are based on treating this as a dual porosity material, and Olga, for one, doesn't believe this is true, but nevertheless, that's what they did, and their FEM results show that there are interesting things going on the intersections. So clearly, there are some things you can do by creating an artificial structure in which you have these kinds of intersections, and that should go in the list of the catalogue of things that you can exploit if you're trying to design a material from scratch to do a target absorption job. And this is showing that something is going on that isn't the same as the mechanism that's usually attributed to dual porosity, which is diffusion of pressure from the big pores into little ones. So here, something that Thomas will be pleased to see, or I hope he's pleased to see it anyway. So he and his student have been trying to create materials based on some of the ideas I suggested a couple of years ago. And they've managed to 3D print, albeit with some difficulty, 0.2 millimeter wide slits. And then they did an interesting thing. They had a look at what would happen if you perforated this assembly. So I guess this is not so much different from perforating the fused metal spheres, but at least you've got a rather simpler geometry to deal with, or you have in principle anyway. What is interesting is that the perforations, these quite sizable perforations in diameter compared with the width of the slits, move the low frequency absorption peak to a lower frequency, which is always something that you're looking for in a thin layer. And they've been able to model it by using the representative volume elements to deduce the Johnson-Champoux-Allard parameters needed to predict the absorption. So I had to go at seeing what you could do to try and reproduce this by having intersecting slits and cylinders, because basically if you take set of slits and you perforate them, then you've got intersecting slits and cylinders, at least to my naive way of thinking you have. But of course it gives something that's quite different from what's predicted by Thomas and his student. And even if you incline the perforations, it doesn't produce the same kind of effect. So something else is going on, which would be quite interesting to investigate. Yet another way of changing the absorption of a material, and this I suppose is related to the valve balls, which Thomas is introducing into his 3D printed materials. This is introducing partitions. So one thing the partitioning does of a bulk array of porous, a bulk layer of porous material, is it ensures local reaction. So it's very easy then also to predict what the diffuse absorption coefficient should be. But it does something else as well. I mean, these various types of partitions change the absorption in different ways. Again, I don't think the people who published this have actually published any experimental results to show it. So there's obviously room for people to look into what each of these different things will do. But the publication that I used to produce these plots actually looked at partitioning a fibrous metal material. So what I've done is I've looked at partitioning a slit pore material, and you get similar results, of course, but clearly it would be easier to, or in principle, it's easier to do this partitioning with a regular type of material. And the number of things it gives you, which you can deliberately change, assuming you could manufacture this, enable you to do any kind of change you want, really, with the absorption coefficient spectrum, which I think is quite interesting. Those were vertical partitions, and the same people, I think, have published about horizontal partitions. And again, they put their horizontal partitions inside a fibrous metal. At least that they did that from the simulation purposes. Again, I don't see any experimental data in these papers. But the horizontal partitions can also do a similar thing. And what is interesting about these horizontal partitions is they also predict the possibility of some kind of metamaterial behavior in the lower layer. This is shown in these plots here, where you can see that the frequency dependence of the so-called equivalent fluid normalized sound speed in each of these layers has a quite different behavior in terms of the lower layer. And also, if you plot the real part of the equivalent fluid bulk modulus for this partition system, then in the lower layer it's becoming negative, which is one of the things that happens for metamaterial behavior. I think this is attributed in the papers to some kind of resonance that's going on, that these horizontal partitions are creating side branch resonances, I suppose, not that dissimilar to the dead end pore structures that Philippe was talking about. So here are my conclusions, and I've shown you all how to give this talk in less than 20 minutes.
Yes.
Yes,
Are you going to read
Kirill.
the conclusions, or I just leave them on the screen?
I'll just leave them on the screen. Well, I suppose I've got 2 minutes to read them, so I do it. So, increasing tortuosity is a way of improving the absorption, low frequency absorption of a thin layer, because essentially what you're doing is in the same way as Philippe was describing, you're slowing down the sound speed within the material so it effectively becomes thicker. You can increase the tortuosity in several different ways. You can incline the pores, you can make them non-uniform, you can intersect them, and you can use combinations of all these things. Another way you can do it is by partitioning, or at least in principle. I haven't yet seen the experimental data, but partitioning, either vertical partitions with gaps underneath some of the alternating vertical partitions, or horizontal partitions, which also give you the additional parameter of the slope of the edge of the horizontal partitions, can also change the absorption behavior. So here is a totally different way, it seems to me, of designing a microstructure to give you a target absorption performance. Thank you very much.
Thank you, Keith. So I guess we've got plenty of time for questions. Any volunteers?
They're all stunned.
I will. Hello, it's Thomas again here.
Yes, Thomas.
I have a comment rather, but it will concern definitely additive manufacturing technology, because Keith actually he would like us to 3D print these micro slitted absorbers. So he would like to have a razor blade separated with slits with a thickness of a razor blade. So it is impossible to do it using 3D printing technologies. But what is important maybe to comment here is that first we tried to manufacture this micro slit absorber using SLA technology, but we had a very big problem getting rid of the resin from the slit. So eventually my PhD student Kamil Obiela, he used our FlashForge Creator Pro FDM 3D printer, and he achieved this. Obviously, if you take a look at, if you remember the picture, the slit was thinner than the size of the nozzle. So it is achievable. Obviously, the wall between the slits, was at the size of the nozzle or something like that. So sometimes the choice of the 3D printing technology is not so obvious, because we wanted to do it with our new SLA printer, and eventually we finished with our old FDM printer. So this is a comment. Please, there are a lot of these kind of problems involved when you want to manufacture your samples. Thank you.
Case one comment came from Francois Xavier Bicot. I don't know if we have a chance to read it. He sent a reference to a paper they published, which is, I think, relevant to what you've done as well.
Okay, I'm trying to get onto the chat.
It's
Right.
it's a JASA paper on the modeling of viscous thermal dissipation in heterogeneous porous media.
Right, 2015. Okay.
I don't know if you have a comment on that.
Well, I'll look at it. I haven't looked at it yet so far.
Anybody else?
Maybe just one more comment. John Kennedy here from Trinity. Very interesting stuff, Keith, and I really agree with you that we should be maybe looking at the defects and maybe how to use them in a beneficial way rather than anything else. And I think that, you know, I'm sure Thomas will agree here that sometimes we're designing things that are not geometrically suitable for the print process. So just for example, the SLA processes, we're really using voxels, which are kind of cubic units, but we're asking them to make cylinders and things like this. So, you know, you can't really make a cylinder out of cubes. And I think if we design our microstructures to suit the 3D printing process, we might get a lot more benefit and a lot more accuracy.
Yes. Do I have something to respond to this?
No, I'm grateful for that comment. I'm glad that at least one person agrees with me.
Yes, maybe the general threat. You see, a lot of these efforts are going now to reduce the thickness of the absorbers.
Yes.
So in comparison with wavelengths, I mean, has any effort been done to produce something like what his name, the guy from Cambridge who developed this famous chart on the structure or the density against the porosity thing. So just produce a chart of different technologies. So how the reduction in wavelengths or in thickness actually compares against the technology.
No, I think that would be a useful exercise. I mean, you can do it. I mean, I've done a kind of literature review of all these so-called metamaterial configurations, but typically,
yeah, Mike Ashby, that's the one.
Yeah.
So thank you, Francois Xavier. Mike Ashby.
Yes, I think that typically the ones that involve on convoluted paths and arrays of resonators tend to be a lot bulkier than I'm talking about here. I mean, at one point, one of the papers was talking about a 1 centimeter thick layer, and typically I'm not looking at anything bigger than a 3 centimeter thick layer, whereas some of these metamaterial configurations, you're talking about at least 10 centimeters in order to fit in the complex resonator structure that's needed.
Okay. Anyone else has a desire to ask a question or make a comment?
Sorry, there's one other thing I meant to say which left my mind while I was saying the other things, and that is, what's his name, Peng, is it? The very famous Hong Kong Polytechnic or Hong Kong University person, Sheng, that's it, Sheng,
Okay.
who's published a lot on metamaterials, acoustic metamaterials. He says that in the end, there's not much better you can do than fiberglass. I mean, I've been present at a couple of talks where he's said that because his structures tend to be the order of 10 centimeters thick, he says, well, 10 centimeters thick of fiberglass will do just as well. I mean, it's pretty good absorber. So I think there's room for, as I keep urging, a totally different approach, which the opportunity for which is presented by 3D printing.
Yeah. Well, maybe if somebody, we've got 69 people now. I had 71 at some time. So maybe it's a good idea for somebody to lead on a review of this, to produce a table like Ashby. So, and maybe think about where all this going, because I guess 3D printing getting more and more accurate. It's getting to micrometer scale soon, probably. So we can design structures which have a very different physics to what it's currently have. Yeah, maybe it's for somebody to lead on this.
Just a comment, we have already 3D printers with which we can really print. They are called nano 3D printing or something like that, but this is really very expensive. Professor Venegar, I think he does a lot of research on that topic.
Well, here you go, see? Because once you get to sub-millimeter, sub-micron scale, so then the physics become very different. And that opens opportunities to make these absorbers, controlled absorbers, more compact, perhaps. Anybody else?
I may have one comment to react on what Thomas just said. Yeah, of course, now we have more and more printing techniques that tend to be extremely accurate. I think one of the main problem is like, I would say, merging the scales. So, for example, printing on an accuracy relative to a micrometer, but printing actually centimeters thick samples that's I think one of the main reasons why it's so difficult, because it's very hard to have such accuracy, but to have macroscopic samples on the order of few centimeters, because it requires first a lot of time and a lot of effort to realize such structures. And I also wanted to join Keith on this point regarding tortuosity in his concluding remarks. Is that from what we have seen regarding the optimization of porous media, we of course have this variation of tortuosity across the layers. So we sometimes observe this, I would say, impedance matching properties. So you have a very low resistivity material at the where the wave impinges, and then across the depth of the layer you have this material which tends to be more and more tortuous and more resistive. But we also observe sometimes the opposite. So when you have a layer which is highly resistive in the entrance of at the beginning of the material, and then it becomes looser in the bulk, I would say. So we observe those gradients of tortuosity that impact a lot the absorption, and at least for small layer thicknesses. That was just a small comment I wanted to add. Thank you.
Thank you. I think probably the way forward is a combination of what Philippe has presented and what I've presented. In other words, you can play both the tortuosity and the compressibility in order to achieve your target performance.
Mm-hmm. Yeah, because it allows you, as you said, to actually have a lot of possibilities to tune the sound speed and the effective layer thickness relative to the wave propagation. So yeah, that may be, I mean, coupling that with anisotropy properties, and you talked about metamaterials and also using defects as an inherent and as an advantage can be very, very interesting. You're right.
Thank you. Shall we pass the floor to Andrew Kennedy?
Yes, please.
Andrew, ready when you are. Andrew, your microphone is mute. Andrew, your microphone is mute. Oh dear. Send unmute request. Okay. Andrew, you have to unmute your microphone. Is only me, or actually anybody else can't hear Andrew?
No, I can't hear him either.
Can't hear you.
Andrew, you have to do something about your microphone, I'm afraid. I did send him request to unmute, but I can't unmute him because probably it's something to do with the hardware.
Kirill, send him a message. Perhaps he can't hear you either.
Okay, so I'll send him a message. I essentially sent him a message request already, but I'll do it now. So Andrew Kennedy. Okay, I've done it. I think he's probably trying to fix something with his sound. So while he is fixing this, how you find this format of conferencing, people?
Well, so far it seems good.
Yeah, I think it's okay, isn't it? It's okay. It's working actually. It's so important in this time of crisis to stay in touch. And a lot of conferences have been cancelled.
By the way, I believe that perhaps more people participate in our webinar that we were supposed to have less people to participate in our workshop.
Yeah, possibly because not everybody can travel, whereas actually getting to the talks via this way is probably the future, is a combination of the two.
You know, while in a face-to-face conference, there are possibilities for you know, networking and one-to-one chat, but this method seems to work very well. And as Thomas and others said, it gives the opportunity for more people to join in. We would not have expected to have 70 people in the workshop if we had organized it as it was. So there seemed to be a place for this kind of online webinar in the future, even when the lockdown is ended. Certainly, it works very well.
Exactly. So I just I'll send a message half an hour ago to everybody saying if you want to present, well, it doesn't have to be such a well-organized meeting. Just want to give a talk on topic of your choice, get in touch with me or Keith, and we organize it for you. It's not a problem. A lot of people will connect. I'm pretty sure about it.
I was wondering, while we're waiting for Andrew to fix the technology, whether some of the questions that are on chat could be answered by the presenters. Someone pointed out quite early on, Paul Murray, that we've been looking at absorption coefficients, but in order to understand what's going on, you better look at impedance spectra.
Yeah. Anybody has a urgency to respond to this? Well, I think it's correct, because if you look at the classical book on sound absorption technology by Morse, so you find actually a lot of discussion is about impedance, how the real imaginary part of the impedance should be matched, or get them matched to reduce the reflection. So discussion about how impedance behaves probably is a good one to have, rather than just focus on absorption only.
Yeah, it's Paul here. Yeah, I was thinking where you have the occasions where your absorption coefficient is going up and down, it's probably in the region of a resonance where your resistance is going below or above 1. So having the real and imaginary components can help you understand what's going on, what the trends are, whether you're generally less than 1 rho C or above 1 rho C at a resonance, for example.
Yeah, you're right.
Another question.
Sorry, Keith, after you.
Another question in the chat is from Rustan Tayong. It's a question really for Philippe Leclerc. And he suggests that one way of looking at discrepancies between simulation, FEM simulation and data would be do a parametric study using the FEM. Since it's likely that the sample hole and dead end dimensions must have changed during the 3D printing.
Philip, do you want to respond to this?
Yeah, Keith, I just heard the question. I didn't find the chat. Yes, I see the question. Yes, he's probably right. And the study I presented it was quickly done, but obviously it needs a more systematic and more precise study. Again, in my presentation, it was just to show that we could find microporosity features and parameters that could give better results for comparison. But of course, he's right. We need to be more systematic in our study and redo the FEM modeling. Also, I saw a question from Tammy about measuring this microporosity. And I think he was saying that perhaps we could 3D print one single plate and measure the porosity. And I think it's a good idea. We might face still some trouble in precision, but the idea is, I think it's a good idea. Anyway, they probably these parameters, the surface microporosity. Is he back? So I'm finished.
Andrew, are you back? Andrew? Sorry, guys. I think he tried to get back, but his microphone keep getting back to mute.
There's another question from Lara Flanagan in the chat. It's for Thomas and Philippe, wanting to know if there's any post-processing done on the FDM samples, as the results showed from UTC before and after impregnation had significantly improved.
I have already answered, Lara.
Yeah, right, thanks. I got your answer. Thank you very much.
Yeah, but I would like to repeat that we experiment a lot with our FDM printers to get this very high quality, as you as you perhaps noticed, it is not so easy to get very good high quality samples with this technology, and the impregnation was applied to samples sintered from the polymer powder with large grains, not so fine grains that we used for our SLS samples. And it was done in France in UTC laboratory. And I have one comment, practical comment for all of you who are going to use 3D printing to manufacture your samples. If you experiment a bit or a lot, as a matter of fact, with your printers, you may expect what kind of discrepancy you should have when, for example, you print at least some typical structures like cylinders or spheres. So when you have some kind of predictions and you say you have some kind of optimization and you say, okay, this geometry is perhaps the best, then you can maybe change, you know how to change it a little bit to get the final print closest to this geometry. For example, you need to enlarge some diameters. So this is a practical comment.
Andrew, are you able to talk now to us? Or are you just, Andrew, your microphone is on mute. Say something. If you hear us, can you say something? I think you say his sound is very intermittent. So is obviously it's a problem with connection. It happens sometimes. So which is a pity it happened to the speaker. So what we're going to do with this, I suggested him to dial with the phone. So and then you can show his slides, talk over the phone, a separate speaker.
Tell him where to find the phone number.
Or he just dial the phone number is at the in the same link, which is on the web. I can send him the phone number for this if he has trouble to access it. I guess it's a problem with the technology. So when it doesn't work, it doesn't work. For example, I try to log in IOA website. They only run weekly IOA meetings online. I can see them really well, but I couldn't hear whatever they say. So, which is a pity. No matter what I try to do, they use Zoom. Yes, do you know his phone number or email address?
Yes, okay, I'll send him an email and copy to you.
Send email, connect via the phone.
Yes.
In this case, can share your screen, which is silent, but talk over the phone, over the slides.
His system has crashed, he says in an email.
Oh dear. Well, in this case, shall we just can keep the discussion going, case?
Yes, okay. I just want to send him this email about the phone if he can get his system up.
because I can share his slides myself, because I've got his copy of his slides somewhere.
right.
He uploaded them on the on
Yes.
Google Drive. By the way, Camille, can you upload your slides as well? Because I haven't done it yet.
I uploaded them this morning.
They don't appear there, Keith. I don't
right.
know, maybe you put them somewhere else.
All right, I don't know.
I will send you another copy of the presentation.
Well,
Oh, please
Camille,
do now.
you have the link to the upload, the Google file, so try direct uploading yourself. I did it
Okay.
via a different message.
Well, I've got Andy's slides.
Am I back in? Can anybody hear me?
Oh yes, who's that?
I hear you. Yeah.
Is that
Andrew Kennedy? I'm speaking.
great.
Yes. I'm not sure how successful I will be.
Your slide.
The sound is pretty awful. Can anybody hear me? Is that it?
I can hear you. It's fine.
Yep. Yes.
I can hear you too.
I can hear you.
So try going ahead.
It's very intermittent. It's yeah, okay. I'll just try and share my screen. Can you see my screen?
Yes.
So I had to shut everything down. It just completely crashed.
Well, that's a problem, I guess, technology. When it works wonderful, when it doesn't, it's a bit of a nuisance. But okay, it's all yours, Andrew.
Can you see full screen or not?
Not yet.
That's the problem having multiple.
Do it on the slideshow. Just click on the slideshow.
Yeah, it's my problem of having multiple screens.
Yes, well, I started life with an IBM Luggable.
If there is a problem with multiple screens, and you can just run it in, run it like you run in a normal, like now. Just zoom on it.
Right, I'll try and I'll see how far we go with this. At the moment, the sound is terrible and I keep dropping out. So I'll see how we go. Can everybody hear me and see my slides?
No, all good, all good.
Okay. So sorry about that, everybody. I want to give a fairly sort of a reasonable overview of our approach at looking at digital design, manufacture of macro porous structures, with a real emphasis on multifunctional performance. So one of the most useful initial things really is around the definitions of the materials. We can be talking about open cell or closed cell materials. From the perspective of functionality, then we're really interested in open cell structures that allow, obviously, the transport of various different media through them. And it's important to make the distinction between the two in terms of the terminologies. So our open cell structures are rather like a sponge, and our closed cell materials are rather like the froth on a decent pint of beer. In the context of sound, we recognize the structures on the left-hand side as being the sort of structures that have been traditionally used as sound absorbers. But within the metal foam community, actually the structures on the right-hand side have been used as well. And that might sound a little counterintuitive because they're closed cells. But in fact, the manufacturing process and post-processing causes the cell walls to crack and perforate, and they become reasonable sound absorbers as a result. I'll chat a little bit more about this later when we move forward. The next slide really shows, the central image shows the types of applications for which foams are used. And in we basically have on the right hand side, we have the load bearing structures, which are predominantly closed cell phones, and they relate to those images on the right hand side. And they're used in lightweight structures, in transport, construction, architecture. They have good energy absorption properties as well, so they're used for impact and ballistic protection. On the extreme left-hand side, we've got the very open structures, the porous metals, and these are really used for thermal management, heat storage, filtration, catalysis type of applications. And in the center ground, we've got sort of partially opened or limited interconnectivity between our porosity, and those are the sort of things that are currently being used as sound absorbers and biomedical implants. So people in the community are really looking to try and widen the applications for these materials, and that's really around trying to exploit the multifunctionality with of course a view to increasing performance and achieving weight and energy savings in a wide range of different applications. The figure at the bottom really shows the difference between the three different key areas. So those around the properties of good ratios of strength and stiffness to density make structures ideal for lightweight design. The stress strain curve characteristics give properties that are good for energy absorption. And the intersection of the two is where applications in automotive arise around lightweight structures with impact protection. They're also been shown to have good mechanical damping, and we know they have sound absorption capabilities. And again, some of these, the intersection between these two gives rise to things like machine tools for particularly sort of vibration damping applications. However, it's really in the center, the absolute center ground, the intersection of these three, where we need to look at high levels of multifunctionality for these sort of structures and materials to outweigh more traditional materials like wadding that's used for sound protection, or honeycomb structures, or other novel materials. But to do that, we do need a novel approach to structural design, and that's really what I want to try and highlight here. So in the context of sound absorbers, you know, we would look at an innovative material as having the potential to replace a complex and potentially costly multi-material structure. So as these absorbers are capable of bearing load, they could function as structural or semi-structural parts, with the added benefits of fire retardancy, impact protection, perhaps electromagnetic shielding, other properties. We could see that they could have very wide-scale applications. They're already being used in some of the images below, show some of the applications where they're already finding themselves. Semi-structural parts for sound absorption in sports centers and concert halls, the linings of train tunnels, and there's some semi-structural partitions and sound deadening within train structures. We can also see that perhaps we could use them as both structural and aesthetic components, which also provide acoustic performance in high-tech audio equipment. So our overall approach really is to look at broadly at this sort of challenge, and the challenge really is around balancing the fraction and the geometry of the porosity to fulfill the function. In this case, we might be talking about sound absorption, and the structural performance. And often these are conflicting. You know, we usually want as much metal as possible for structure, and maybe as much porosity as is possible for fluid flow or minimizing pressure drop, whatever that might be. What we find that traditional porous structure manufacturing processes don't give us the chance to vary all the different structural parameters that we need independently. So it means we can't change pore size and connectivity and porosity and do a very detailed study of what the important factors are. This approach also has variability to the manufacturing, meaning it's quite difficult to study individual components in a rigorous fashion, and it can often be quite costly. So the way we propose is to use a sort of virtual environment for this, using digital design and manufacturing. Typically, it's sort of the approach shown in the figure at the bottom, generating a 3D model by a number of different means. I'll talk about that in a second. Applying modeling approaches in physical and mechanical systems, generating our physical model through things like 3D printing, and then validating the model, the physical model and the modeling. And if we go through those iterations and come up with something that's sensible, we then do need to address how we can translate that into a scalable manufacturing process. We might find that 3D printing or additive manufacturing is a sensible approach for some niche components, but it's not likely, and we'll have to resort to conventional approaches if we're trying to build structures to line train tunnels, for example. So our prototyping approach really is as follows. You know, we look to create a digital structure, to manipulate that structure within a 3D CAD environment, and then we split into an STL type of file that we can use for 3D printing, or create a representative volume element for the purposes of FE modeling. Obviously, the other side of the modeling, we have the analysis, and we could go through a feedback loop to optimize the structure. And on the other arm, from the printing side, we have a physical model that we test. The importance, of course, is relating our physical testing results to our analysis through some sensible validation. And when I come to the end, I'll talk a little bit about some of the challenges that lie there. Oops, I hopped right back to, yeah. So it makes sense to look at what the actual structures of porous materials are at the moment. And commonly, they're either made by burning out a polyurethane foam. We coat a polyurethane foam and then burn out the residual polyurethane. That gives us these traditional open structures that look like traditional polyurethanes. But they can, and people have already been talking about this, we can end up generating structures which themselves have some porosity. And one of the figures at least shows a very textured surface on that porous structure. And on the right-hand side, an alternative route is we cast a metal within the holes that separate things like salt beads. And we dissolve or flush out the salt in warm water, and we create structures where the walls are very, very solid. So we've already talked a little bit today about how we need to really match the things that we build to the structures that we might be wanting to use in our parts, and I'll come on to that a little bit later. But then we do see that there's a commonality in the structures. They both types of approaches give us sort of nearish spherical pores in a fairly broad, the potential for a fairly broad size range, and they're connected by round-ish windows within typically the ranges of 100 to sort of 700 microns in size. So we can create digital structures in a number of different ways. What we found is a good approach is to use different methods to create 2D slices, which we can manipulate if we want, and then use that to reconstruct a 3D volume, which can be done in many different off-the-shelf software packages. So we can take actual samples, we can scan them using micro CT, produce slices, and then reconstruct those slices to produce a 3D volume. Alternatively, we can use a discrete element modeling method to produce a packed bed of spheres, and again slice that and reconstruct. And the warming thing here is that we see that actual real parts and our structures made from DEM models look very, very similar, which gives us confidence that these sort of artificial packing models are pretty good replications of the real structures. We can manipulate these structures as well, so we can use For the case of CT and DM, we can just do simple image analysis of our as achieved structure, and we can dilate it and erode it and then reconstruct it. With our DEM models, having X, Y, Z coordinates for all the spheres, we can apply all sorts of algorithms to shear or morph or squash particles together to alter our structures. We're currently looking at, so that those can reflect random structures. We can also look at ordered structures, and that's where we're diverting some of our attention at the moment. And as we've seen in other studies as well, it's quite a popular approach. I'm picking up really on the packing of things like BCC structures, which you see on in the black and blue model. The packed structure becomes the inverse, and that becomes the porosity in these sort of models. And we can tailor the overlap of the spheres in that packed structure to vary the degree of porosity and interconnection. And by using Python or similar coding coupled with CAD packages like SolidWorks or SpaceClone, we can then multiply these structures up, and we can even do space filling as well. So on the right-hand side, there's an example of an arbitrary image, of this case of a bone, and that's filled with a series of these inverted BCC elements. Of course, then we get to the point of needing to print a 3D version of our model. And it's worth stressing that in many cases, the application will require large parts made in metals, and AM isn't really likely to be able to deliver these sort of large parts and the sort of volumes that people want. But of course, the AM and 3D printing is really vital to this virtual prototyping approach. Having said that, metal technologies, some of which are shown down here, are improving, the quality is going up, cost is coming down, but the resolution is still rather limiting to a really detailed, comprehensive and accurate study of the influence of structure on performance. There's already been some evidence today that shows actually the structure is more important than the material itself. So in fact, we could take other approaches, and we currently prefer the approach of 3D printing in polymers. I've said here we can create polymer analogs that are cheaper and faster. We've got some quite expensive machines, but actually some cheaper SLA machines produce very good results as well. Our better machines have much higher resolutions than metals, sub 20 microns. Metals are governed, and SLS of polymer powders is governed by the powder size, and we've got much better resolution by these jetting printer type systems, and examples of which are shown in pink at the top. But we also get good accurate structures using SLA, using curable resin systems as well. Some examples are shown at the bottom for ordered and random structures. So if we go on the premise that the structure is the same, flow really doesn't see the material itself, we can go about through our, obviously people are familiar with the sound absorption approach, but also fluid flow or pressure drop measurements as well. People might be slightly more concerned that when you come to mechanical and thermal properties, one would say that the material, matrix material, would be incredibly important. Some examples are shown here for mechanical testing and thermal testing based on thermal imaging. But in fact, for both of these types of properties, the scaling laws that are shown at the bottom apply very well. So that means we have a sort of normalized value for like the modulus or the thermal conductivity based on the ratio of the behavior for the foam compared to the behavior of the solid material. And these then relate to the relative density of the material, the ratio of the densities, and the constants relate to really the architecture of the structure. So it means that actually we can study the performance based on the architecture alone, and it can be system independent. Then, of course, there's important elements around the FE modelling. Here's some examples of meshing and modelling of mechanical performance of these porous structures, typically looking at stress distributions and predicting stress-strain curves from them, usually the early stages of them. When you get to high strains, it becomes very, very difficult. But it's clear that you've got, from these type of responses, particularly for ordered structures, you can apply inbuilt systems within things like ANSYS to do structural or topological optimization, to do further improvements of your modeling designs to make them more structurally efficient from a mechanical perspective. Similarly, there's good modeling to be done on fluid flow, obviously meshing the inverse of our structure, the gaps between the material. And again, looking at pressure distributions to integrate with things like Darcy's law to look at the permeability, and looking very keenly at the changes in permeability as a function of architecture. So at the bottom, we show flow streamlines, and we can get pressure drops from the same analysis or similar analyses as a function of the level of connectivity between the structures. So the size of the gaps between the spheres, and we can look at local perturbations in flow, and we can look at more global effects on the pressure drop and the permeability of the system. So modeling without validation is just numbers, or indeed numbers and pretty pictures. We need the confidence that we can apply a high level of modeling to develop optimization without a very large need on producing samples. And we've had some good examples of successes in modeling thermal behavior, pressure drop. The models are the lines, and the experimental data are the dots, and they match up very well. And also had some good successes around sound absorption as well. So where does that leave us? It still leaves us with some fairly significant research challenges. Creating and manipulating digital structures requires a flexible framework to generate the structures and manipulate them and get them ready for the next modeling steps. And this can be computationally very demanding, particularly if you're trying to create real structures. And we're looking intensely at trying to modify these approaches to make them as simple as possible. Within the modeling area, we're looking at modeling different properties at the same time as being our final goal. At the moment, we're just looking at one at a time. Really, we would like to overlay these and be trying to optimize for a number of different parameters within the same modeling framework. There's been lots of comments today about the importance of measuring and knowing what you're printing and how that relates to your model. Part of that is choosing the right materials and having good process control, but obviously part of it is making accurate measurements of the parts that you're printing and relating that to your models to give you confidence that actually what's coming out of the system is what you're putting in. Analysis-wise, a system for good optimization really needs some interpretation of the many factors that come out the other side of modeling, and representing them in easily digestible graphical formats. Things that are easy to interpret in the forms of maps to allow you to pick and choose your parameters that give you an obvious balance between the properties you're looking at. Otherwise, you've got to dig deep into a lot of very complex data. Of course, the physical testing perspective, we're doing a lot of work around trying to ensure that the representative volume elements that we are using are representative of the bulk, and that depends on whether we're looking at highly random or ordered structures. And of course, testing wise, there's an importance to make sure that we are conforming to ISO standards as well. And when we look at this whole thing together, then there's a real importance on striking a balance between fast and accurate modeling. Already some of these problems require access to high performance computing networks, and it would be nice to try and make this more of an accessible framework than something that's very esoteric. So the overall outcome we hope really is that we can look to a modeling based framework for aiding us in the design and manufacture of multifunctional porous materials, and the step from that, looking at even more focused applications, is then integrating porous elements within bulk structures. I'd like to first of all thank you for listening and for your patience given my initial IT shortcomings, and would welcome questions.
Thank you very much, Andrew. So we've got quite a few minutes for questions before we need to conclude at 1 o'clock.
Yes, I mean, there's no harm in concluding before 1 o'clock if that's possible, but I just wanted to comment, of course, again, you're starting, Andrew, from the kind of microstructures that are commonly produced for bulk manufacture. So do you see any role from starting instead to design a microstructure which satisfies all the requirements that you lay on it?
I think, yeah, I mean, it's quite a sort of philosophical question, that. I mean, there's a difficulty trying to reconcile the manufacturing routes for different types of products. If we're looking at sort of high volume applications, I think there's no way that we are likely to use additive manufacturing to deliver the products that are required. So you could, I mean, people have talked about design for additive manufacture as a way of building up these structures, but they're still going to be quite niche. To deploy them in transport applications, where they've got obvious benefits for noise reduction in aircraft, impact protection, whatever it is, we're going to have to adopt scalable manufacturing processes, and they are not likely to involve 3D printing and additive manufacture. So the perspective we've been looking at is really trying to move a little bit back from the structures that are typically used and looking at how we can sensibly modify them within a framework which is realistic in terms of actually manufacturing them on a bulk scale. Did that answer the question?
Yes, but I have another question that follow on. I mean, what about envisaging structural elements which incorporate, for example, sound absorbing structures? So let's say you're making a vehicle panel. Is it possible to envisage etching or whatever other process could be used to create a porous lining which satisfies the requirements for the acoustic performance?
I think retrofitting something like that is difficult. I think, if you were talking about part of a audio speaker system or part of a structure in an aircraft, you would probably be looking at manufacturing inserts elsewhere in a porous structure and then embedding them into the larger structure themselves. With the modeling approach, looking at where the key locations for those components might be.
Okay, somebody else must have a question.
Yeah, I have one comment to make on your slide number 13, if you can go back to this one. Thank you. Because I've actually tried printing this unit cell on, slide 13, yes, this one. So the pink one. I've been trying to print such material, and I've been stuck with something. Is if you decrease the pore size to a few hundred microns, what happens with SLA is that you get stuck. Because actually it can be difficult to extract the residual fluid inside of the structure, and then this resin starts to coagulate, and you get stuck with a kind of an inclusion, a rigid inclusion inside of your structure. So it was just a small comment on this point, because it's pretty interesting to be able to have this cheap manufacturing, but if you tend to go lower in terms of pore size, you can get stuck into those problems. So this was just a small comment. And I had a question. I've seen you've been using micro tomography techniques. I think it was on slide number 9. Can you give me an insight on what was your voxel size, the resolution?
So, so the voxel size on these are typically at around 15 to 20 microns.
Okay. Okay, thank you.
So reasonably decent resolution. I mean, it's all obviously about balancing resolution versus frame of view.
Of course,
we could go to higher resolutions, but we are still looking at the importance of the RVE size for modeling, and for these random structures. Unfortunately, we need quite big RVEs for them to be size independent. So yeah, it's juggling that balance really between the level of detail. There is, the reconstructed image does actually involve a level of smoothing, and of course, as people have spoken previously, we need to check that once we've smoothed that, we go back to our original structure, we haven't created any artificial
of course,
artifacts that are going to improve, that are going to deviate from reality. Your comments about the printing on 13, I mean, I agree completely. We've got a mixture of different systems, and we use a number of different resins to try and improve the removal of the resins, and we can use a number of different flushing systems to try and flush it out. So once you restrict the permeability, inevitably you can have some issues. And we get some quite good results from daylight curable resins as well. But the system on the top is a polyjet system which deposits a support material, so we can go down to smaller sizes, albeit on an expensive machine, which uses water-soluble support. And although it takes a while to get all of the support out from the very finest of channels, it is achievable, so we can get finer detail in those systems. That being said, when you look at manufacturing processes for metallic foams and porous metals, the smallest apertures tend to be of the sort of 200 to 300 microns in diameter. So again, it's a philosophical question. Do you design something that you can never make, but actually is the perfect absorber, or do you sort of move back a bit and say, well, actually, I'm stuck with a series of current manufacturing processes. I have to sort of work within that framework to see what changes I can suggest to improve the performance. On that basis, there's a lot of materials used as sound absorbers which are far from ideal. They're just there because they can be made. All of the stuff that I showed for the train tunnels are really just closed cell foams that have been whacked with a hammer to perforate the cell walls. And they are what they are. People have done nothing to optimize them. They're really just, they're used because they can be made. There's still a lot of potential for improvement in these materials.
Yeah, I agree. In fact, that's what we tried to optimize this absorption. We actually want high tortuosity and high resistivity, and which implies small perforations, small pore diameters, and this is where we get stuck using those printing techniques, because even by applying pressurized airflows, we got stuck actually trying to remove the residual resin inside of the layer. But yeah, it was for pore sizes between I think it was 300 to 400 microns. And I just wanted to point out something very quickly. On the slide just above, you talked about binder jetting techniques. Can you tell me a bit more about this? What have you tried with these techniques, if you have even tried something? And what can we achieve with those printing techniques?
So, I mean, I think some of the important discussions today, and even relating to what you've said with the fine porosity, is that the different techniques offer different conditions for the cell walls. So, with our SLM process, we will have fairly solid ish cell walls, the same as we would get from SLA or the polyjet resins. But the binder jetting is basically like an old, it's like this sort of Z-core version of jetting a glue onto a bed of metal powder.
Okay.
So that product needs to be taken out of the bed and then sintered, and you can still have quite a lot of residual porosity in the cell walls. And it may be that once we know more about the system and the modeling, that actually having the residual porosity in the cell walls, like you would have in something like that people have shown happens in things like SLM of nylon or whatever else, SLS of nylon powders and similar. It actually might offer us a better alternative than trying to engineer small apertures sort of on purpose. So the digital metal is spraying a binder onto a bed of powders, and at the bottom there are industrial systems based on FDM or FFF, whichever is your preferred name, and again they will produce partially porous structures as well. So again, understanding and modeling what you're likely to get is important. Understanding what the porosity is of the primary channels compared to the porosity within the cell walls is key as well to accurate modeling.
Okay, I understand. Thank you. That's all for me. Thank you very much.
So the digital metal stuff is pretty expensive. Yeah.
Yep.
Hello, I think Francois Xavier, you had a question as well about slide 18. Francois Xavier? I wonder if he signed out now. Andrew, maybe you can just read this question later on and respond to Francois Xavier.
Yeah.
Okay.
Acoustic velocities. Yeah, I'm not quite sure what these. So these are all separate studies on 18. So the pressure drop measurements are on an high velocity airflow system. Just to clarify, the sound absorption stuff is taking Darcian-based permeability values, as people have discussed already today. The two plots there don't really have any bearing. They are separate studies. One going way beyond Darcy into the onset of reasonably turbulent behaviour, and the other really using other measurements that we've made at very, very low speeds to generate laminar flow conditions for permeability measurements.
Okay. So, Kiss, I mean, unless there are some very urgent comments, shall we just wrap it up? Kiss?
Yeah. I apologise again for my IT issues.
No, I understand. We clapped to you.
I was poised, ready for action from before 9 o'clock, and as soon as it was my moment to shine, then that's when everything went terribly, terribly wrong.
And it happens. I mean, it went wrong this morning when I realized we tried to use the wrong version of GoToMeeting, which limits the number of participants to 11. Anyway, so we'll here to sort these problems out. And it's good everybody connected. So we had 70 odd people at the time listening to the talks. So it's a great achievement in my view. So that all of you gave your time to present and to organize it and to attend it and to ask questions. So I don't know, anybody who would like to make some final comment?
Just a quick one. I just got an email from some person from Poland who couldn't attend to the conference and asked me for the link. I do not know this person, by the way, who asked me for the link to listen to our conference. So the audience will be even larger, but please provide us with the link.
Yeah. Well, actually, I sent you a link already, Thomas. It's in the chart. So,
okay,
but
so this is the same
it's also
for the registered versions. For the registered version, it is this. Okay.
No, it's actually I send you again. So basically, it's in here. So I just send it to everybody. Well, I also you can find this link if you go on Acoustics AC UK resources, and I think there is a link to webinar series presentations. It's not only for this one, but all webinars we're organizing. So anybody who shares presentation with us will find copies of this presentation on that link. Okay.
Sorry for my silence, Kirill. I was temporarily crashed, but
okay. Well,
I'd like to thank all the speakers, and I'd like to thank everyone for participating in this. And I think it's been quite useful and eye-opening session. I hope you all agree.
Yes, and also I'd like to thank you for organizing that, and Olga as well. So it's one of the biggest virtual conferences I took part in, and it by and large just I think it went well. So just the final one. So if anybody wants to give a talk, please do. Also, I do recommend you to go on the Acoustics AC UK website events and look at other webinar series, and some of them quite nice about machine learning in acoustics, about boundary integral equations in acoustic, and so on. So it's not the last one; it's one of the first ones, but there will be many more to come. Okay.
Yes, thank you for chairing this, Kirill.
Oh,
I think
pleasure.
it was very useful and well organized conference. All the best to everyone.
Thank you, and stay well. Exactly, stay well, stay away from trouble, and hope to see you in person rather soon and later. Okay, I stop recording now.
Okay, bye.
Thank you very much. Bye. Thanks.
Bye.